ಕೋಡಿಂಗ್ ಮಾಡಬೇಕು. ಓಕೆ, ನಿಕ್ಕಿ ಮೈಕ್ ಬರ್ತಿದ್ಯಾ? ಆಡಿಯೋ ಬರ್ತಿದ್ಯಾ? ಆಡಿಯೋ ಚೆಕ್ ಚೆಕ್, ಮೈಕ್ ಚೆಕ್. ಅದು ಇಲ್ಲೋಡು, ಗುರ್ರಿಂದ ಕಡಿಮೆ ಮಾಡು.
The poster should also come. I have gone live. So HTML output illa. And the keyboard question.
ಕುಮಾರ್ ಕುಮಾರ್ कुमार को चॉक पीस करना और साइंटिस्ट और
It will come. No. Actually, they will switch. Actually. Yes, sir. Just explain. Yes, sir. Yes, sir. Just explain. Technically explain. It's okay. Driver come. One second. Hello, one second. Check. Hello, check. One second. Just leave this. Is this computer audio?
Check. Hello, hello, check. Check. Hello, hello. Check. Hello, hello, hello. Check, check. Check. Hello, 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 hello. Check, check. Very good detected. Check, check. Hello, hello. Testing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1 second. Check, check, check. Check. Hello, 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 hello. Check, check. Hello, hello, hello. Check. It's cannot connected. Check. Hello, hello, hello. Check, check, check. Hello. Check. Check. Hello, hello. Check, check. Check. Hello, hello, hello. Check, check. Hello, 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 hello. Check, check. Hello, check. Hello, hello. Check, check. hello, hello, check, check, hello, check. Check, hello, 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 check, hello, hello, check, check, hello, hello, check. Check, hello, 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 check. Check, 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 hello, yes, check, hello, hello, check, 1, 2, 3. Check, hello, check, check. Okay, check, hello, hello, check, check, check. Yes. Check, hello, hello, check, check. Volunteer, check.
Okay. I have one as a chair. Wow.
Because the speaker, while he's speaking, people will be coming. No, that we need to disable the waiting room. No, no, waiting room we need. So,
Check.
அது work ஆகும். இது work ஆகுது.
Sure. Shall we start?
Hari, look, it's not in the
Okay, welcome everyone to the 34th International Conference on Formal Power Series and Algebraic Combinatorics. It's wonderful to see everyone in person after 2 years of online conferences. Actually, it's difficult to believe that so many people are here. Actually, in around the beginning of May, I was sure that there'll be 10 people in this room, and but it has finally turned out, and I'm glad everybody is here. Thank you all for coming. The last 2 months have been have seen a lot of combinatorics related events. We had a satellite workshop on combinatorial algebraic geometry last month, where June He was one of the invited speakers, and he had accepted last year, but as his life, he could not accept this year because he happened to go to Helsinki for some reason. Next week, we are going to have Sage Days as part of a satellite. So, last week, there was a conference on combinatorics and graph theory in Coimbatore, to which some of you attended. So, yeah, so anyway, so it's great to see you all, and I hope all of us will have an enjoyable conference. So let me give you some brief logistical tidbits. So there is no smoking on campus allowed. Okay, so if you need to smoke, you need to go outside. There is a lift facility in just outside the foyer. So those of you who need to use it can use it. We are supposed to have masking in the lecture hall. Last two other events have seen COVID clusters, so we do not want that to happen. So please wear masks. Restrooms. So the men's restroom is on this floor. Just as you exit this room, it's on your left. The women's restroom is half a floor down. So we have reserved e-rickshaws for transport to and from the guest houses for those who need them. They will be there for the entirety of the conference. In particular, if you want to use it to go to and from the breakfast and lunch venues, you can feel free to use them. Please wear your badges during breakfast and lunch so that you're not questioned. About food, we have asked the caterer to mention all the food allergies that we have received in the during the sign up sheet. But if you are at any point doubtful, please ask. So the main caterer will be available. He speaks in English, so you should not have a problem. If you need translation, ask one of the Indians around. Okay, so I remind you about the code of conduct, which is there on the website, as well as in the brochure. Yeah, please follow the guidelines over there. Okay, so now for some good news. So thanks to generous support from funding agencies, we will be able to subsidize, we will be able to pay for your banquet as well as your excursion. So I hope this is being recorded. I want, I want to show, and I hope the applause is also recorded. So they should know that we appreciate this gesture very much. So I know that most of you have filled in the online form, but I ask all of you during the breaks to fill up the sheet which asks you whether you will come for the banquet and or the excursion and or the classical music concert on Saturday. So please do fill it. We will take that as the final count. Okay. Both the banquet is about 12 kilometers away, so we'll arrange buses, and we need to know how many people are there to arrange buses. The excursion is to a beautiful Jain temple called Shravanbelgola. In Shravanbelgola, it's a statue of Bahubali. That is about 250 kilometers, I think, away. So that will take maybe 2.5 hours, maybe a little more. So that is on Wednesday afternoon. And the conference banquet is on Thursday evening after the special lecture on Indian combinatorial history. Okay. Okay, so guidelines about hybrid meetings. Please raise your hands during the talk if you need to ask a question. The reason is, I mean, we will give you the mic and you can ask your question. And I should say, before I forget, that I welcome all the online participants as well. For the online participants, if you want to ask a question, please raise your hand. Sorry, please type your question in the chat. We have volunteers viewing the chat and sitting with the chair. So they will show the question to the chair. If the chair deems it relevant enough to interrupt the speaker, he or she will do so. Otherwise, the questions will be taken up at the end. All talks should be n-5 minutes, where n is the time given in the schedule, so as to give us 5 minutes for question answers and changing the system. So the poster boards will be ready by the tea break or tea or coffee break during mid-morning. For those of you who need to print posters, there will be the poster printer will be here soon. He will give you instructions on how to send your poster if you want to print and the cost. Okay, so I think I'm done with all the introductory remarks. So it gives me great pleasure to welcome our first chair, who also coincidentally, it's a complete coincidence. It has nothing to do with the fact that we designed the schedule. The first chair is also the PC, one of the PC co-chairs. So welcome to Svante Lunason. I hand it over to him.
So hello everybody, and welcome. And as one of the PC chairs, I'm very happy to have so many people here, and very grateful that we have been able to have such a strong program with such many interesting talks and posters. And every year there's also many good, strong submissions that we have to reject. And that's a very strong sign for the Fpsac conferences. That just keeps getting better and better. So Fpsac is really an amazing opportunity to learn and to find new problems and new collaborations. And I hope that all of you will do so during this week. And then, as a sign of this strong conference, I am happy to introduce our first speaker, Professor Omer Angel, who is now getting his microphone. And his slides should be up soon on the board as well. So Omer is professor at University of British Columbia in Western Canada. He's a fantastic mathematician and probabilist, and all of us who had the great fortune to collaborate with him knows that he's a man full of ideas and a very fast thinker, and is also giving very good talks. And I'm very much looking forward to hear what he has to tell us about how to find even subgraphs in infinite graphs within an i.i.d. probability. So, okay, are you ready, Omer?
I think so.
Yes, yeah. Good. Okay, so please welcome Omer Angel as the first speaker.
Yeah, so thank you, Arvind, Linus, Svante, and the rest of the organizers. It's wonderful both to be here specifically in Bangalore again and to be able to travel again and see so many people I hadn't seen for a long time. In fact, the very last trip I had before the pandemic was to Sweden, to the Mita Gleffler Institute, and both Svante and Arvind were there. So it's a bit of closure. Okay, so are my slides? No, they're not on yet. Okay, and is this a clicker? Okay, seems to be working. Yeah, so I should also mention, as the title of the conference is Formal Power Series and Algebraic Combinatorics, there certainly will be some power series and algebra and combinatorics in the talk, though not maybe in the sense that you think about. I am generally more a probabilist than a combinatorialist. So this means my background is different, and the things that seem obvious to me might not be obvious to you, and vice versa. So I do encourage you to ask questions and stop me if anything is clear, and if there are some things that I'm glossing over that should be explained, then let me know. There are some parts of the talk where I will certainly not be able to go into full details. So generally what I'm going to talk about is some work from the last couple of years about factors of i.i.d. in the context of some models of statistical physics. This is work with my former student Gura Brai, currently at Victoria, and Inon Spinka, a postdoc at UBC. Is everything okay? And I don't know. We could just ignore this. I don't think there's anything terribly important in the at the very top of the slides. well, okay, we'll manage without this. Okay, so basically the plan for this talk, the first section of the talk will be about even subgraphs of given graphs. The second part of the talk will be about factors of i.i.d, the other big topic in the title, which is something that comes from ergodic theory. It's a concept that turns out to be very interesting and also has some relations to statistical physics, as it turns out. The third part will involve some of the motivations for looking at all of those things. So I'll discuss several models of statistical physics, and I will define those fairly quickly, but I'll try to give you all the necessary definitions. And this is also the main motivation for us for looking at random even subgraphs. And finally, I'll finish by saying how we can reconstruct these even subgraphs. So yeah, okay, so this is obscuring the title. So I guess a lot of titles of the titles will be slightly obscured. I prefer to keep it on. If can people hear me with the mask? Yeah, if everyone can hear me, then I prefer. In a closed space with lots of people, I prefer to keep the mask on. Okay, so I'm going to start by talking about random even subgraphs. So what are even subgraphs? Is there a projector here? I don't know if the red dot is visible, maybe especially on Zoom, but okay, so we have some graph. This is just an arbitrary graph. And an even subgraph is just a subgraph, so a collection of edges, so that all the degrees are even. So you have degrees 0, 2, 4, all are even. That's the only constraint. So that's what an even subgraph is. And if you have a subgraph, well, if you have a graph, then any subgraph you can encode by 0, 1 on every edge. So 1 if an edge is included, 0 if not. So that means that subgraphs are naturally correspond to Z2 to the space of edges. And this gives us, thank you. That's, no, that's, I think there's more interesting things at the very bottom than at the very top. So at the top, I just have a title, which sometimes is the same from slide to slide even. Hide floating meeting control. Yeah, excellent. Yeah, so okay, so yeah, the pleasures of being the first speaker. Yes, so okay, so subgraphs are in bijection with Z2 to the edge space, to the set of edges. What happened? So now the clicker. On there? Yeah, so this stopped working now. So I can just go here. I see, yes, okay. It was just the focus, yeah, it's working now. Okay, so so because of this connection with Z2 to the E, there is a natural vector space structure here. So that lets us talk about sums of subgraphs, where if you add subgraphs, everything is added mod 2. So if an edge is included, so we have the subgraph on the left and the subgraph on the right, both are even. And if you add them, then you get the subgraph on the right. And it's easy to see that if you take even subgraphs and add them, you get an even subgraph. So that means that the even subgraphs are a basis. I need to, but I already know how to do this. Okay, let's hope it stays gone. So this is the space of even subgraphs, which is also called the cycle space. The reason it's called the cycle space is that it's spanned by cycles. So you have those two cycles, you can take other cycles, and the subspace generated by them is the even subgraph space. So that's what happens for an even for a fixed graph. And for now we are thinking of finite graphs. Later we will talk about infinite graphs, and there are several interesting things that happen there. But still, for finite graphs, suppose we want to pick uniformly a random element of this cycle space. So we want to pick a uniform age. Okay, so it's a finite space. There are lots of ways to do this, but here's one way. I can take some basis B. So this is true in any vector space over Z2. So you can take a basis B, and you take independent uniform epsilon i's. Okay, this is not going away permanently. Control Alt Shift H. So we have some basis B, and we take coefficients epsilon I, which are uniform either 0 or 1, and we take the sum of epsilon I bi, and this gives us a uniform element. This is true for any vector space over Z2. And something that should be corrected here. So actually, the distribution of the result does not depend on which basis you take. That's also easy to see. That's basically linear algebra. But B doesn't even need to be a basis. B can be any spanning set. So it doesn't have to be a basis is a minimal spanning set. You can have some extra elements in B, and this will still be fine. And the distribution of the element that you get will be uniform over H for any spanning set B. So this all is some nice simple things you can do with finite graphs. But what happens when you take infinite graphs? And when you take infinite graphs, things become a bit messy. So these are infinite dimensional spaces, and you have to be a bit careful. So the simplest example of an infinite graph, we can consider connected graphs for now. The simplest example is something like Z, the infinite line. And for the infinite line, well, you can see there are no cycles. Right? There's certainly no cycle that you can take. So the space spanned by cycles is just the empty graph. But there is one other even subgraph of this, just the whole thing. So in this case, we have just two even subgraphs, either the empty subgraph or the full subgraph. And okay, it's only two, so it's also clearer what it means to take one uniformly. But this is sort of too simple an example. So the next example is maybe something like the infinite ladder graph. So for the infinite ladder graph, we already have quite a lot of even subgraphs. So we have the cycles, and the cycles are basically the individual squares. Or if you take a cycle which is slightly longer, a cycle that goes around 2 squares, well, this is actually just the sum of the cycles that go around the 2 individual squares. So you can take the subspace spanned by all the cycles, and this is a well-defined space of this infinite dimensional space. But this does not include every even subgraph. For example, if you have the subgraph that includes just the top line, so this cannot be written in any way as a sum of cycles. And then you can consider other things like the grid, like the two-dimensional grid or higher dimensions. And again, you have lots of cycles here, but here it's also, there's a question, can any even subgraph be written as a sum of cycles? So it turns out that when looking at infinite graph, and this is something that you see a lot in many other settings in statistical physics. Sorry, there's one more example I want to mention, which is a regular tree, or it doesn't even have to be a regular tree, but if you have an infinite tree, then again, there are no cycles, but you do have lots of even subgraphs. So you can take any doubly infinite path, and that would be an even subgraph. So something that happens in many models of statistical physics, when you want to define things on an infinite graph, well, you start with something that is well defined on finite graphs, and then you take limits. And there are two types of limits that are the most common to appear. They're the free and the wired limits. So what is a free limit? So the free limit, you take some subsequence of finite graphs, say call it Gn inside G. So we have some infinite graph G that we are interested in. We take a finite subgraph Gn. And now we can take a random even subgraph of Gn. So Gn is a finite subgraph, so it's so we know exactly what it means to take a uniform even subgraph of Gn. And now we want to take a limit, and this is a distributional limit of the Hns. So what does the limit mean? So you can ask for every set of edges, you can ask what's the probability that these edges are included or excluded from H. And these probabilities for any set, these probabilities converge as Gn goes to infinity. So this is a theorem. It's not a very difficult theorem. It can even be an exercise, but I will not prove it. So this limit exists. So this means that again, for any set of edges, if you ask which of those edges are included, so the probability that certain subset of these edges are included in H converges as Gn grows and becomes the whole graph. And the limit also does not depend on the choice of the Gns that we take. So that means there is a natural distribution on even subgraphs of the limit graph. And this is called the free limit. And the reason it's called the free limit is to distinguish it from what is called the wired limit. So the wired limit is a similar construction, but we do something slightly different at the edge. So we take a finite subgraph Gn, and now you define Gn star by contracting everything outside of Gn to a single vertex. So this is a picture. If you take, for example, the square grid, and suppose that Gn is some box inside the square grid, then you can contract everything outside to a single vertex, which has a very high degree now. It's connected to everything along the boundary, sometimes even with multiple edges. That's fine. So this is a finite subgraph. This is a finite graph now. It's not a subgraph of the original one, but it is a finite subgraph. So we can talk about the uniform even subgraph of this Gn star. And again, so we can take a uniform even subgraph Hn in Gn star and take the same limit as before. And this is called the wired limit. So wired because the boundary is all wired together to a single vertex. And again, same as for the free limit, the limit also exists. It does not depend on the choice of exhaustion. And this gives us two limits, two distributions on random even subgraphs of a graph G. One is the free limit, one is the wired limit. Now, sometimes they are equal, but sometimes they are not. For example, if you take the line Z, so I'll put maybe a few small things on the board. I don't know if is this visible on Zoom? Will this be visible on Zoom? Yeah. So for example, if you take the line Z, so if you take the free limit, so the free limit you take just a finite interval, and this has only one even subgraph, the empty graph. So when you go to infinity, you just get the empty graph always. Whereas if you take the wired, so the wired one, you get one extra vertex and you get a cycle. So now you have two subgraphs, either the even or the empty or the full. And when you take the limit, you get with probability half the empty subgraph, with probability half the full line. So in the case of Z, the two limits are not the same. One of the free one is just always the empty graph. The full one is with half and half. But sometimes they are the same. So for example, for the square grid, the two-dimensional grid, so for the ladder, they are also not the same. For trees, they are not the same. But for the two-dimensional grid, it turns out that they are the same. And it can be a bit tricky in general to determine if someone gives you an infinite graph, is the free limit the same as the wire limit? This is not, it's something you have to think a bit about, depending on the graph. Sometimes it's easy, but not always. Now, since we were talking about these vector spaces, I should mention, so in some sense, you can consider those as uniform elements on the following vector spaces. So you can define the free even subgraph. So this is the subspace of subgraphs of the infinite G that are spanned by all of the finite cycles. So you have every finite cycle, they span the subgraph of this infinite dimensional vector space. And that's the free even subgraph space. The wired even subgraph space has additional spanning elements, included, which are doubly infinite paths. And so, okay, and those two spaces may or may not be different. So, so in the case of trees, for example, the free even subgraph space is just always the empty space, just 0, but the wired includes all doubly infinite paths. So it includes also sums of doubly infinite paths. So these are the free and wired limits. And yes, so, okay, so that's an exercise figuring out what happens on Z squared. And finally, one more comment before moving on to the next chapter. So I mentioned this construction, given a basis or a spanning set inside inside the space, you can generate a uniform element by taking uniform coefficient epsilon I and taking sum of epsilon I bi. So this also works for the infinite subgraphs. So and we'll come back to that later when we look at some specific examples. But you can take some basis for one of those spaces, take random coefficients 0, 1, and the sum gives you a uniform even subgraph. So that's a lot of background about even subgraphs. The next big figure in this talk is factors of i.i.d. And this is something that comes from ergodic theory. It's a fairly significant notion. And let's start by thinking about two processes, xn and yn. So you have two random processes, xn and yn, indexed by the integer z. And we do assume, I did not write it, we assume these processes are ergodic, so invariant to translations and well ergodic. So, so x is called a factor of y. If you can compute x as a function of y, so you can find some function phi so that if you apply phi to x, you get the process y. And phi needs to be translation equivariant. So what does this mean? It means if you take the process y and shift it, so you just shift everything by some distance, and you apply the function phi, then you just get, the result is just shifting the output of phi. So, and okay, and the special case of this, if y is just an i.i.d. process, so just independent and identically distributed values, just all independent, then x is called the factor of i.i.d., so which we abbreviate f_i.i.d. So let's look at some simple examples. So one example, suppose yn is whatever process, xn can be the set of descents. So xn is 1 if yn decreases and 0 if not. So x is a factor of y. If y is i.i.d., then it's a factor of i.i.d. So the locations of descents in this i.i.d. sequence is a factor. Another example, you can take the maximum of 3 consecutive elements. So if xn is the maximum of those 3, or you can take larger windows, or you can take some windows of variable sizes, then this is again a factor. Another example, you can take xn to be 1. It's a location where y satisfies some condition. And you can take any condition you want, but the key property is that the condition should not depend on the location. So if you translate everything, then the condition should also be translated. So for example, here I'm asking that that if you move distance m away, then you increase by at most m. So these are points that are relatively large in some sense. And there's nothing special about this this example. So this is again a factor of the process y. And you can take any function that you like. Finitary factors are a special type of factor. And these are a factor which has the following property. So suppose you want to try to compute x at a specific value. So you want to determine x at a point 0. Then you start looking at y of 0 and y of 1 and y of -1. You start observing the values of y in some order. Doesn't really matter what order. And a finitary factor means that at some point, which might be a random time, at some time you can say, okay, stop, I've seen enough. And now I can tell you what is x of 0. So you don't need to look infinitely far. At some point, you say, I don't care about the other values, anything away from this, and I know what is x of 0. And if you want to compute x of n, then it's exactly the same because of the equivariance. So you just start observing values starting with yn and observing from there. And you will also at some point be able to stop and determine the value of x. So, so the first couple of examples I had before are finitary factors. In this case, even the stopping time is very small. So for this one, you can stop after observing those 3 elements. For this one, this one is not finitary, because if you start observing values of y, well, maybe at some point you find some value of y, some value of m which violates this, and then you know, okay, x is 0. But if you have not observed such a thing, then you have to keep looking, and so you might not be able to say stop at any point. Well, okay, so this depends actually on the distribution of y, but if y is bounded, for example, then at some point you will be able to say, you know that, so if y is, so if the y's are between 0 and 100, then after you observe the 100 elements, you can stop. But if the y's are unbounded, then you are not able to stop. So these are finitary factors, and it turns out a major problem that in many cases people are struggling with is understanding which processes can be written as factors of other processes, specifically of i.i.d, and what properties can these factors have. So can they be finitary? And if they are finitary, how far do you need to look before you stop? And there are many other properties that I'm not going to get into. So the examples I gave you before are for factors when the processes live on the line. So you have the integers z, and you have for every n, you have xn and you have yn. But this makes sense also for processes which live on some other graph. So you can consider some general graph G, and you can consider a process which lives, for example, on the vertices of G. So for every vertex V, we have some value xv. That's a process. And we want to have the same property. So x is a factor of y if you can write x as some function of y, which is equivariant. So if you apply some isometry to the graph G, so for example, if the graph G is z squared, and you translate everything by some arbitrary amount in an arbitrary direction, you get a factor. Similarly, if you take a regular tree and you can apply some isometry, so that means every label moves to some other label with some isometry of the tree, and you apply the function phi, then you get the same function of x. And again, maybe simple examples, you can look at something like the maximum of the, say, the label at the vertex and the neighbors. That's a simple example, but there are much more complicated ones you can come up with. And the final comment, these processes, I write everything on the vertices, but sometimes we want to put randomness on the edges. That doesn't really make a difference. So let's look at some less trivial example. Suppose we take the square grid, and now we take what's called Bernoulli percolation on that. So every edge is included with probability p independently of all the others. So I take here the blue edges are the ones that I include, and p is maybe 0.3 here. So you have maybe 30% of the edges on average. So this gives us a random subgraph. And now I'm going to assign each cluster. I look at the connected clusters, and each cluster is going to be either red or blue or green, sorry, with by a coin toss. So some clusters are red, some are green. And now I forget about the edges. So I had the subgraph where every cluster had one color, but now I forget about this. So now I no longer have a way of knowing whether this edge here was present or not. So this gives me a process. So these are a process. I have a coloring of the vertices, red and green. And the question, is this a factor of i.i.d? So is this, can you describe this process? Can you construct this process by taking some i.i.d variables at the vertices or edges of the original graph and doing some operations which are determined locally. So that's a question, and this is already, turns out, not completely obvious result. So it turns out that if p is small enough, and there's a critical PC, which in this case is a half, then all of the clusters are finite. So we have these clusters that were drawn here, and they're all finite subgraphs. And in that case, it's possible to get this as a factor of i.i.d. And really, the i.i.d, the independent variables are shown in the construction. So you have this independent variable for every edge saying if it's included or not. And then, for example, you can say for every vertex you have a preferred color. But then when you have a cluster, you can say, let's look maybe at the bottom left most vertex of the cluster. And this vertex determines the color for the entire cluster. So these are i.i.d variables at all of the vertices and edges, and using those, I have constructed this process. But if you have an infinite cluster, and it turns out if P is greater than a half, then you do have an infinite cluster here. Then for the infinite cluster, you don't have any way of determining the color. There's no bottom left corner. There's no invariant way of choosing the color for this cluster. And in fact, in this case, it's not going to be a factor of i.i.d. It turns out that if you were to do this, there has to be some way of breaking the symmetry, and the infinite cluster will have either green or red. So that means that either most vertices will be green or most will be red. They will not be half and half, but the symmetry is broken, and the factor of i.i.d cannot do that. So that's what happens on the square grid. But you can ask, and so already on the square grid, you can see that whether something is a factor of i.i.d depends on some properties of this percolation, which are certainly non-obvious property, non-trivial properties of percolation. But what happens if you do this on other graphs? So you can do this not just on the square grid, you can do this in higher dimensions, you can do this on regular trees. And again, something similar happens. If you have only finite clusters, then the exact same argument, basically the construction I gave for this process X shows that it is a factor. If you have one infinite cluster, and on ZD, for example, if you have an infinite cluster, there will be only one, then the same sort of argument shows that this is not a factor of i.i.d. But then what happens if you have infinitely many infinite clusters? And for example, on the regular tree, you have infinitely many infinite clusters for some values of P. And in that case, we do not know. And this is open in general for this specific model. So that's so this somehow shows that whether a process is a factor of i.i.d depends on some delicate properties of the process. Okay, and at this point, I'm going to move to a sort of a whirlwind tour of several models of statistical physics. But are there any questions before I move to that? Okay, so I'm going to talk about several models. I'm going to start with the Ising model. So going back to the 1920s, this is one of the most classical models of statistical physics, a model for magnetism. I will not go into the connections, but the configuration here, so this is a model which it can live on any graph. And you have some configuration, sigma, which has plus or minus 1 at every vertex. And if you have a finite graph, then it's defined as follows. So the probability of a configuration sigma is proportional to e to the beta times sum of sigma x, sigma y, where the sum is over all adjacent pairs. And beta is some parameter. It's called the inverse temperature. So what does this mean? If you have nearby vertices x and y, if sigma x is equal to sigma y, then you get a positive term here. So the probability of configurations where nearby terms are equal is higher. And if nearby terms are different, the probability is smaller. And how much higher and how much smaller depends on this parameter beta. If beta is large, then we really make a lot of effort to make nearby things equal, whereas if beta is close to 0, we don't care as much. And that's what you can do on a finite graph. These are some examples of what happens if you do this on the square grid. And as with the percolation, there is some phase transition here. So if beta is small, then you get something that looks roughly random. You get the picture looks very similar to just if you toss a coin for every vertex. And when beta goes to 0, it's exactly just a coin toss for every vertex. Beta goes to 0 means all configurations are equally likely. There is some critical point where a lot of very interesting things happen, and this is certainly the most interesting part. I'm not going to talk about this. If beta is larger than beta C, then you get some clumping and you get some large regions which have just one, either all, not all plus or all minus. Actually, you'll have inside this region of white, you have some island of black, and if you have a large enough island of black inside it, you'll have some islands of white. So it's not just a simple picture like that, but you get some, for example, you get very strong correlation. So you get the two vertices that are relatively far apart will still be significantly correlated. So, so that's the Ising model. And that's on a finite graph. On a finite graph, I told you how to define the distribution. But you can take an infinite graph, and on an infinite graph, you can take, again, free and wired limit. You can either take finite subgraphs with no boundary, that's the free limit. Or if you have the wired boundary, you can think of having one more boundary outside. This is like a boundary condition. And if you have this external vertex, you put a plus on it. This is called the plus configuration. So mu plus is the measure that you get if you put a plus on the outside, mu minus if you put a minus, and mu f is if you put nothing on the outside. So again, these are the limits of what you get from finite graphs, where you put these particular boundary conditions on the outside. So for mu plus, it's a plus boundary condition. And these limits all exist. This is, again, not an obvious statement. And one of the biggest questions, whether these limits are all the same or different. And that is the transition at this beta C that I mentioned. So if beta is larger than beta C, then the limits are not all the same. Whereas if beta is smaller than beta C, then the limits are all equal. So if beta is beta C, somehow the boundary conditions far away do not matter. Okay, and this has been understood. So there's some work, some results of Ornstein and Weiss, and generalized by Adams to general amenable graphs, that the plus measure is a factor of i.i.d. For any temperature beta. And this was extended by RL and Spinka to more general models beyond the Ising model. You need some monotonicity property. So in contrast, there is a result of Vandenberg and Steiff on the square grid ZD. It's not, mu plus is a finitary factor of i.i.d. if and only if mu plus is equal to mu minus. So if beta is small enough. And this again shows that whether you can construct this process as a finitary factor of i.i.d. captures some of the physical properties of the model, and in particular, this phase transition that happens at the critical beta. And I will not go into the reason why, but we can discuss this later if anyone wants to. So that's the Ising model. And the Ising model, again, you can consider this on any graphs. So the most interesting graphs that have been studied historically are grids, two-dimensional, where there's a lot of magnificent mathematics has been done. That has a lot to do with Schramm and Smirnov's Fields medals even. But in 3 dimensions, things are very exciting as well. Higher dimensions too. You can do this on regular graphs. And again, on regular graphs, mu plus is, okay, it's a factor of i.i.d. as we said, but it's a finitary factor sometimes, but not other times. There's several results here. The free one, again, sometimes it is a finitary factor, sometimes it is not a finitary factor. And even though on the tree, this is a relatively simple model, we do not even know where exactly is the transition for this to be a finitary factor. So there are several different transitions that happen here, and this is things that people are still trying to understand. There is still a gap where we don't know what is the answer, whether it is a finitary factor or not. Okay, let me skip this gradient Ising since in the interest of time. But I will tell you an important property of Ising, and this is the FK Ising model and the Edwards-Sokal correspondence. So if you have a finite graph, the FK Ising is closely related to Ising, is the following distribution. So you have a configuration omega, which is a configuration on edges now. And the probability of a configuration omega, so you have a factor of p for every open edge in omega, a factor of 1 minus p for every closed edge. So if you have only those two, then this is just percolation. You just have independent, each edge open with probability p, closed 1 minus p. But there is an extra factor here of 2 to the number of clusters in omega. And these 2 also can be generalized to a q, but for now, let's stick with 2. So you look at the number of connected clusters, and you prefer configurations with many connected clusters. So you tend to have more closed edges. And you can take free and wired limits of this. And these are phi f, phi w. And those are factors of i.i.d. That's a result of Hagstrom, Jonasson, and Lyons. And in some cases, they are known to be finitary factors. In other cases, they are not. But again, I'm going to be moving on. But there is an important correspondence due to Edwards and Sokal, which connects this random configuration omega on the edges with the Ising model. And it's very similar to what we discussed earlier. So you have this random configuration of edges, maybe something like this. And you do exactly what we did before. Each connected cluster, you toss a coin and make it either +1 or -1, red or blue in this picture. And now you forget the edges. So if you take the FK Ising with this probability on the weights, with this probability on the configuration omega, and you apply this procedure, you end up with a +-1 configuration. Turns out what you get is the Ising configuration in the distribution is the Ising configuration with some parameter beta, which is related to P. So that's the Edwards-Sokal configuration. Now, okay, so time is running, so I'm not going to go into as much detail about what is the Lupo-1 model. I'll just say briefly, so this is a configuration, this is a random graph where you have configurations eta on edges and vertices. So you have 0 or 1 on every vertex and 0 and 1 on every edge. And here we start connecting to the even subgraph picture. Because of this, this is the distribution that you get on finite graphs. So if you have a finite graph, the probability of a configuration, you have x to the sum of the edge weights, and you have y to the sum of the vertex weight. So you have a weight of x for every edge that has a 1, y for every vertex that has a 1. But we have an indicator that it's an even configuration. So what is an even configuration? This is just like the even subgraph. So for every vertex, we want that the sum of everything involving the vertex is even. So the sum, this means all of the edges, including the vertex, plus the eta of the vertex itself. And maybe one way of thinking about this, so you have the graph, and you can think that you have this one axis outside vertex, which is connected everywhere, and the eta v tell you whether the edge to this external vertex is present or not, whereas the eta e tells you whether an edge is present or not. So then you just have an even subgraph of this extended graph, the original graph plus this outside vertex connected everywhere. Okay, and we have free and wired limits, and as I wrote here, there's a special case. If x is 1 as y is 0, then this is just the even subgraph of the original graph. Since you have nothing on the vertices, and so you don't care how many edges you have. Okay, and we can understand some things about when this is and is not a factor of i.i.d. And in particular, we can show, this is one of the main results of this work. So the wired measure is always a factor of i.i.d., except for one setting, if X is 1, Y is 0, and G is a two-ended subgraph. And I'll just state quickly. So what does it mean two-ended? The number of ends of a graph is the maximal number of infinite connected components when you remove a finite set. So if you take the two-dimensional grid, if you remove a finite set, you have only one infinite connected component. If you have the line or a ladder graph, you can remove a finite set so that you have two infinite components. So those are two-ended. So the wired one is not, and remember, X equals 1, Y equals 0 means just the uniform even subgraph. So in this special two-ended case, the wired uniform even subgraph is not a factor of i.i.d, but in all other cases it is. For the free one, we know that it is a factor of i.i.d in many cases. So it's a factor of i.i.d whenever Y is positive for many graphs G. If it's amenable, if it's planar, there's some other condition that I will not discuss. We believe it's always a factor of i.i.d, but we are missing some more general construction. So these several cases are just based on different constructions. And the way we prove this theorem, the main idea is by a connection with the Lupo-1 model. So the Lupo-1 was known to be a factor of, sorry, the FK Ising model was known to be a factor of i.i.d. And this is connected to the Lupo-1 in some work of Eisenman, Dominique Copan, and Sidorovicius from about 10 years ago, where they show that there is a strong connection between these models. It's a bit similar in flavor to the Edwards-Sokal correspondence. So given a configuration of the Lupo-1, so it's you have this configuration on edges and vertices. You can just say that every edge that was closed, you still open with probability X independently of the others, and every vertex you open with probability Y. And you get a random subgraph, and okay, and then you need, and this gives you the FK Ising. So this exactly gives you the FK Ising configuration. And given, so that means that the FK Ising contains the Lupo-1 as a subgraph. And the other direction is also simple to describe. Given a configuration of the FK Ising model, you just take a uniform even subgraph of that to get the Lupo-1. Now, the FK Ising model was known to be a factor of i.i.d based on the monotone couplings and the connection with the Ising and so on. So the FK Ising model was known to be a factor of i.i.d. So if we can get the uniform even subgraph also as a factor of i.i.d, you can compose factor. A factor of a factor is a factor. So that will give us the Lupo-1 as a factor of i.i.d. And that is the reason that we got interested in the first place in understanding, can you construct even subgraphs as factors of i.i.d? So the basic scheme will be you can generate the FK Ising and then take a uniform even subgraph of that as a factor of i.i.d. That gives you the Lupo-1. And this brings us to the problem that we mentioned. Okay, so we are given some graph, we are given the FK Ising configuration, and we want to generate, so this is now a random graph, it's not a fixed graph. And we want to generate a random uniform even subgraph of that, either wired or free, and that depends on whether we are interested in the wired or free Lupo-1 models, as a factor of i.i.d. So we want to do something like what we did at the beginning. We want to take some spanning set of either the free cycle space, the free even space, or the wired even space, and take a sum like this, sum of epsilon I bi. But in order for this to be a factor, we need two things. First of all, we need this to be well defined, and this means that the sum needs to be locally finite. If you have an edge that is contained in infinitely many of those bi's, then the sum, this is just a sum over Z2, the sum will not be defined. So we need the sum, so we need this spanning set to include every edge only finitely many times. That's one constraint. The other constraint, in order for this to be a factor, we need to choose these bi's in some invariant way. So you can't just say, here's my set, just have a fixed root and list the bi's, because then if you apply some translation, then your basis will have moved and you are not using the same construction. So it will not be equivariant. So as an example, one of the simpler constructions, if you have a planar graph and you're looking at the free even subgraph space, you can just take the set of faces. So the faces are cycles and they generate, that's a spanning set, and every edge is included in only two faces. So then you can just say, well, for every face, you take either a 0 or a 1 coefficient, and you take the cycle around the face like that. So how much time do I have at this point? 5. Okay, thank you. So, okay, so I'm not, okay, so there's a more precise definition of ends of a graph. So you can talk not just about the number of ends, but about the actual ends. And you should think, for example, of the case of a tree, where on a tree, basically an end is just any infinite path. That's a nice, that's the basic example you can have in mind. And here's a way to generate a basis for a cycle. So we need 3t. So given a graph G, we need a 3t. We need it to be end faithful. That essentially means that every end of the original graph has one end of the tree. So if you're looking at something like a strip, then you need a tree that has one infinite path going to the right and one going to the left. Exactly one in each direction. Okay, so if you have a tree like that, here's a way to generate a set of cycles which are spanning. So I take every edge that is not in the tree and I generate a cycle CE. So how do I get the cycle? I take the edge and then I complete the edge to a cycle by connecting through the tree. So again, I have an edge that, and the red edge is not part of the tree. The tree is in black here. We have a red edge that is not part of the tree. And I can close it to a cycle inside the tree. So this gives us a spanning set for the even subgraph, for the free even subgraph class, provided we can find such a tree. So can we find such a tree? So there is a result of Helin from the 60s that says that every connected graph has an end faithful spanning tree, but we need to choose one in an invariant way. And that makes things more difficult. So there are several results, various cases where it's known that this can be done. In the amenable case, there are some results of Benjamini, Lyons, Perez, and Schramm, and some results of Timar that show that it's possible to construct such trees. The infinitely many-ended case, so this is a non-amenable case, is less clear. So at this point, okay, and I'm not going to go into the details of the constructions given time, but at this point, in some sense, things break down and we no longer have a unique method that works always, but we just have various methods that work in various cases. And we're still looking for some method that works in much greater generality. So another thing that we can do, so the wired even subgraph space is easier to work with. So for the wired one, it turns out that you can take a spanning forest with one-ended trees. So now it doesn't need to be a single spanning tree. We can have several trees. So it needs to be spanning. Every vertex is part of some infinite tree. And every tree has a unique path to infinity. So these are one-ended trees. So suppose you have such a spanning forest. So here's another way of generating a spanning set for this EW space. For every edge that is not in the tree, I'm going to define some cycle CE. So if the two endpoints of the edge E are in the same tree of the forest, then I just do the same as before. I have the cycle completing inside the tree. If the edge E connects to different trees, so I have the left tree here and the right tree here, and the red edge is not in the forest, but it connects to different trees, then I make it into a doubly infinite path. I just take the infinite path in the left tree and the infinite path in the right tree, plus the red edge. Okay, and I claim that these things give us a locally finite basis for the sample space. So why is this locally finite? Well, you can show if you have any edge I claim that any edge only participates in finitely many of those CEs. Right? If an edge is not in the tree, then it only participates in CE, so it's only in one. If an edge is inside one of the trees, then this one-endedness is needed. So if an edge is, so if you have an edge inside the tree, then you have this is some finite configuration, and here you can go to infinity. But because the tree is one-ended, then on one of the two sides of the end, you have only a finite set. So in order to get that this edge E is contained in CE, this only happens if the edge E is an edge that connects like that, either like that or an edge that connects this part to some other tree. So you only have finitely many edges for which this edge here is contained in CE. So it's locally finite. And again, there is a question, can you construct such a spanning forest as a factor of i.i.d? And again, I'll finish with this. The answer is yes. And in fact, there is something called the wired uniform spanning forest. And in many cases, in any unimodular graph, this is such a graph. And this is a factor of i.i.d, which is proved by using the cycle popping construction, which related to Wilson's algorithm. And again, there's a lot more going on behind here, but I think this is where I'll stop. So thank you.
Thank you very much. Do we have questions for Omar? Yes, there's a question here.
Yeah, so I was just wondering if there's a version with directed graphs. So you mentioned, I'm mostly referring to the early parts of your talk. So you mentioned yes, you can construct the subspace of even subgraphs. So I was wondering if you could also define that using directed cycles and a directed graph as well, right?
Yeah. So a lot of things can be defined, and certainly it's a very interesting question to do things in a directed setting. The linear algebra aspects break down. So a sum of two directed cycles with cancellation, mod 2 is no longer a directed cycle. So at least the picture that I painted for you breaks down at a very early stage. So I'll have to think more about what can be salvaged, but it will have to be a very different picture, a very different story from everything I said. It's certainly an interesting question.
Any other questions for Omar? Okay, let's thank Omar again for a very nice and interesting talk.
Okay, so, and thanks again for the invitation. It's a pleasure to be here.
Even to Roger's mother.
Hello, hello. Is that good? Okay. And the sound's not going to come through mine, right? I should have it off. Okay. Yeah. Yeah, I'm not joined on audio yet. Maybe I can. Testing, do I sound good? Great, awesome. Yeah, whenever you want.
Okay, let's move on to the second talk of the conference. And now we have Alex McDonough from UC Davis, and he will tell us about the rotor routing structures on plane graphs. Please.
Right. Thank you very much. Thanks everyone for being here. So this is, the title might look a little scary, but I'm going to have some animations that are going to help out, and I think it's a really cool topic, so I hope you enjoy it as well. This is all joint work with Ankan Ganguly. We were living together in Providence back when I was at Brown, and I told him that he's a probabilist. I told him I had a project that would kind of combine his probability with my chip firing interests. And it turns out I was completely wrong. There's absolutely no probability in this project, but it was still incredibly fun. It was great working with him. So I have some animations to go along with some of this that I'll be flipping back and forth to. And you can find these slides on my webpage if you're interested. So the first thing I want to talk about is I want to define ribbon graphs. So there's some different perspectives for how people look at these, but what I really want to think of them as is just a graph where the edges around every vertex are given some sort of cyclic ordering. And we're going to just always use a clockwise ordering for this talk. So we can think of this as really a drawing of the graph on a particular plane, or you could do it on a higher dimensional surface, or a higher genus surface, I should say, not higher dimensional. So a plane graph is a ribbon graph with no edge crossings. This is like a specific embedding of a planar graph. So I have a couple examples up here of ribbon graphs. The first two are the same graph, but the first one is not a plane graph because you can see that there's a crossing here. You could not draw this on a sphere without some sort of intersection with this specific choice of ordering of the edges around each vertex. The second example is a plane graph because now we've drawn it so that the edge goes around this other vertex. And the third graph is a non-planar graph. So there's no way to get a plane graph from a non-planar graph. So this is another thing that can happen in certain situations. But this is just going to be graphs with a little bit of extra structure, which is going to be necessary for some of the things I define. And now we have this algorithm that I'm not going to give you enough time to read. This is going to be something that we're going to be working with for throughout this talk, and we're going to be adjusting this definition over time. But let's look at an animation to see how this works. So we're going to start with a graph, and we have a spanning tree, which is the solid line. And we're going to choose, there's some vertex that's the sink and some vertex that's the chip. And the first step of the algorithm is that we're going to direct all of the edges towards the sink. And we're calling these rotors. So you'll notice that every vertex other than the sink has one rotor coming out of it. And the way this algorithm works is we're going to rotate the rotor where the chip is, and then we're going to move the chip across the rotor the other side. We're always rotating it one position in this cyclic order. We're working with a ribbon graph, and we can speed it up a little bit and watch the chip move all around this graph, moving around these rotors until we finally stop when it reaches the sink. And now that we've reached the sink, we erase all of the directions on these edges, and we say that rotor routing has gone from that starting spanning tree to this other one. Rotor routing specifically with this choice of sink vertex and this choice of chip. So this is the basic single chip rotor routing algorithm that we're going to be working with. So some facts about rotor routing. So this was originally called the Eulerian-Walker's model. And the perspective was a little bit different, but some results that are implied is, first of all, the final output is always a spanning tree. Even though in the middle of the algorithm, you don't have spanning trees necessarily, as you saw, you're always going to end with a spanning tree. And that's something that you can play around with a little bit to see why it's true. It's not immediately obvious, but once you look at it the right way, it is a very simple argument why that's true. And then another lemma that comes up pretty quickly is that if we do this multiple times, if there's multiple chips, then it doesn't matter what order we move the rotors where the chips are. We can go in whatever order we want. And this brings us to our second clip of the day. Just giving you an example of having the chips moving in different orders and seeing that the same thing happens. So in this case, we have 2 chips. I have some numbers on here, which will make more sense in the future. And I have 3 different ways of resolving this. On the first one in the upper right, I have 1 chip going first. Bottom left, I have the other chip. And then the bottom right, I have the chips just taking turns. And in the middle of this, it doesn't necessarily look like they're all behaving the same way. But if you wait for it to finish, you're going to end up with the same spanning tree no matter what happens. And this is not an extremely difficult thing to show, but it ends up being very important for a lot of this idea. And I also want to mention this paper, Chip Firing and Rotor Routing on Directed Graphs, by many big names in the field. This is the first paper that I read of like real research math papers, and it's a good one to start out with. It's very clear and is the one that really, for me at least, it puts these things in the perspective that I wanted to work with compared to some of the earlier ones had similar results, but a different perspective on it. So now we can adjust our algorithm with our observation from that last animation that we can have more than 1 chip. So, and then we just choose which chip we want to move at each time. We saw that this is well defined. It doesn't matter what order we do it in. And so here's our new slightly stronger algorithm than what we had last time. So next, what I want to do is introduce the Sandpile group, and I'm not going to read all this. I'm going to show an animation that doesn't even use all the same terminology and perspective, but it's the way I like to think of this. So a degree 0 divisor of the graph is an assignment of an integer to every vertex such that they sum to 0. This terminology comes from algebraic geometry. And these are going to form a group under pointwise addition. So if we add 2 of these, add the thing at each point, sums to 0, the final result is also going to sum to 0. And to get the Sandpile group, we're going to introduce this equivalence relation given by firing. And that's just some firing happen right there. So what you do to fire a vertex is it gives 1 chip to each of its neighbors. So every time you see these chips moving away from the vertex, that is 1 firing move. And it adjusts you from the starting position to the final position. And in certain circumstances, it makes sense to only allow firing in certain situations, like maybe you don't want to go negative. The way I like to set it up is you can fire anything whenever you feel like it, even if it's already negative, or you go into negative from being positive. And when you do that, a lot of the algebraic results become simpler. And you can also, this sort of gives another perspective for how you could define this thing. And a very important theorem that is central to all of the things that I do involving the Sandpile group and chip firing is that the size of the Sandpile group is the number of spanning trees of your graph. And we're going to see this come up very soon. So now we're going to give a new version of this rotor routing algorithm where the input, instead of being a collection of chips, is an element of the Sandpile group. And I haven't proven yet that this is well defined. We'll see that in the next slide. So our input now is we take an element of the Sandpile group, and then we're going to choose some representative of that equivalence class that has non-negative many chips away from the sync vertex. And we can always do that. You just kind of fire the sync vertex a whole bunch of times and then fire some other stuff. It's one of those things that if you play around with it a little bit, you should see that this is always possible. The thing that's definitely less obvious is that it doesn't matter which representative you choose. But that's what we're going to see in this next slide, which gives us another animation to look at. So this is a pretty short animation. You see we have the same situation on the right. We're going to move the chip 3 times from this position. And what we end up with is we have all of our rotors are in the exact same position. And it looks like we just fired this bottom right vertex. So this is certainly not a proof by any means, but this should help give you an idea that chip firing is like doing a partial firing. So if you have things that are firing equivalent, they're also going to have the same effect when you do chip firing. And chip firing, when I say it, it's sort of synonymous with the Sandpile group. When you think about it as like firing chips around on your graph. So this is well defined. This is that paper I was talking about earlier, Holroyd and many others. But there's also this fantastic fact that for any pair of spanning trees, there's exactly one element of the Sandpile group that maps from the first tree to the other tree. So this tells us that rotor routing is defining a free transitive action of the Sandpile group on the set of spanning trees. And this for free transitive actions, if you're not as familiar with them, it's very similar to a bijection, but we have a group and we have a set. So the Sandpile group always has an identity element, but the set of spanning trees doesn't always have a special spanning tree. So a free transitive action says that if you tell me which spanning tree to associate with the identity element of the Sandpile group, then we get a bijection. And this is something that's good to look for if you ever have a group and a set that are the same size. So this led to a question on Math Overflow by Ellenberg, who asked, when is the rotor routing action preserved after changing the sync vertex? So if we chose a different sync, how would that adjust this rotor routing action? And it turns out there's a wonderful answer to this, proven by Chan, Church, and Grachow, which is that this rotor routing action is preserved regardless of the sync vertex, if and only if G is a plane graph. So this is where it's important to work with plane graphs and not just ribbon graphs. And let's see this in action. So if we change the sync, we could, for example, fire this vertex in the lower left and then allow it to resolve in either case, allow these rotors to spin around. And as with before, it's not at all clear what's going to happen in the intermediate stages, but once you let it fully evaluate, you end up with the exact same spanning tree. And this is far from a proof, but hopefully this gives you some motivation for why this is true. So any questions so far? Yep.
How do you define the chip firing algorithm when there's a negative number of chips at a rotor?
Yeah, that's a good question. So there's 2 different perspectives. There's the rotor routing perspective and the chip firing. So the way that I do it with rotor routing is I just make sure that all the negatives are on the sync vertex, so I never have to worry about them. So that means that we have a perfectly, I mean, it's not immediately clear that it's well defined, but that's why I show that other animation. But we have this way of dealing with the case is we just take something that's equivalent as an element of the Sandpile group, but has all of the negative chips on this one sync vertex. As far as the Sandpile group, then there's no problem with firing negative things. It can just send a chip over and it's still in debt. Now it's in more debt, but yeah, that's how it is sometimes. Any more questions? Yep.
start with a chip, you'll be able to reach at the sink by doing this router item?
Yeah, that's one of these questions that is, if you play around with it a little bit, it should make more sense. Sort of like you can't really get a situation where you go around forever and never return. There's this perspective involving unicycles that makes all of these things a lot more natural, where you add an extra edge from the starting place of the chip to the sink. And with that perspective, a lot of these ideas come down. So if you look at that paper by HLMPPW, you can get this unicycle perspective, and a lot of these results will follow pretty simply from that. In the interest of time, I think I'm going to continue, and then I'll take more questions later. But thank you for the questions. So we saw this clip 5. So now we have our final version of the rotor routing algorithm, where the adjustment now is we have to input a plane graph. And the first step of the algorithm is to choose a sink vertex and just choose whatever we want, instead of having that be part of the requirement for the input. And so now what we have is, it really is a action of the Sandpile group on the spanning trees. We need a we need some specific like ribbon structure on our graph, and in particular, it's a plane graph, not just a normal graph. We don't need to pick a sink, which is nice. And I have some notation at the bottom. Don't worry about it. That's just so I can write things precisely in the slides. So now we had to do some definitions. There's this idea of Sandpile torsors, which is was first stated in that math overflow question, but hasn't actually been defined anywhere. People talk about Sandpile torsors, but there's not really a precise definition. So what we ended up going with is, we say Sandpile torsor action on a plane graph is some free transitive action of the Sandpile group on the spanning tree. So it could be rotor routing, it could be something else. And then we separate this out from a Sandpile torsor algorithm, which is an algorithm that assigns a Sandpile torsor action to every plane graph. So we saw that rotor routing is a Sandpile torsor algorithm, because no matter what plane graph you give me, I can give you this Sandpile torsor action, this free transitive action of the Sandpile group on the set of spanning trees. And then the question is, so this is pretty natural to state, but it doesn't seem like there's definitely not some other way of doing this. So are there other natural algorithms that we might come up with? So in 2012, Baker and Wang used the Bernardi process to define another Sandpile torsor algorithm. And I'm not going to tell you what goes into this, but it looks very different. It uses break divisors, and it has the same idea where you can define it on ribbon graphs where you need a sink, but then the sink doesn't matter if and only if you're on a plane graph. And this is something that they showed. And in general, on ribbon graphs, the Bernardi process looks different than the rotor routing. You're going to get a different result, even if you choose the same choice of sink vertex. But the really fascinating thing that they showed is that the rotor routing algorithm and Bernardi algorithm are actually equivalent when we restrict to plane graphs. So that's a little bit surprising. And there's a couple other descriptions. Oh, yep. Oh, yeah. So what equivalent means is you get the exact. So the question was, what does equivalent mean? And the answer is that you get the exact same Sandpile torsor action. So if you take the same element of the Sandpile group and the same element of the set of spanning trees, it'll give you the same final result. Yeah, thank you. So there's some other descriptions in this case. These other ones are just sort of other perspectives of describing the Bernardi algorithm on plane graphs, or in the second case, it's talking about this Trinity perspective. And in these cases, there's not another perspective that works with ribbon graphs that have a sink, but you get this same case where these end up being identical. So we keep finding the same thing when we kind of take different paths to look, which is surprising. And this leads to the conjecture by Clivens in her book, for plane graphs, there's only one Sandpile torsor structure. And I know what a lot of people are probably wondering, what does this mean? That's part of the conjecture. Try to figure out what this means and then prove it. Because that's one of the most challenging parts, is to figure out what it means to have like a specific Sandpile torsor structure, because you can certainly just choose whatever free transitive action you want on each graph and have them be completely unrelated, but that doesn't really feel meaningful. So we're looking for some kind of natural action, but we're afraid to use the word natural because then all the category theorists will get mad at us and tell us that's not really what's going on. So that's the first goal, is to figure out what this should even mean. So first of all, there's actually 4 different Sandpile torsor algorithms that you get from rotor routing, because you can just reverse the direction of everything and go counterclockwise instead of clockwise. You can also take the inverse. So you basically treat the sinks as sources and the sources as sinks, or the chips and versus sources, same idea. And this will happen for any Sandpile torsor algorithm. You actually get these 4 possibilities. So we said that these have the same structure. So 2 Sandpile torsor algorithms have the same structure if you can get from one to the other by these, if it's one of these 4 things got by these 2 Z2 actions. And we're still not done. This is kind of nice to have this, but we're so far from having an actual definition of some sort of consistency for how a Sandpile torsor is allowed to react or act. I don't know why I said react. React to the graph that it is given. You could have clockwise rotor routing on some graphs, counterclockwise on other ones. You could have clockwise on some, and some weird thing that doesn't make sense on some specific graph. And the first thing that I came up with when I was first looking at this project, when I was starting in grad school, is to have some sort of automorphism invariance. Like if you have an automorphism of your plane graph, it should still act the same way. And this is good to require. It doesn't get you very far, because there's a lot of graphs that don't have any non-trivial automorphisms. And we still want some way to discuss how the action on one plane graph is related to another one. So this is where I was stumped for many years of trying to figure out some sort of definition of consistency. And we found it. So this is another one that is easier through animation. So what we ended up finding that was true about rotor routing that we in turn made as our definition of consistency is, first of all, so we saw before that this is what happens by rotor routing. We get from the thing on the left to the thing on the right. We're going to choose an edge that's in both of these, and we're going to contract it. And then we're going to see what happens when we do rotor routing. And it's very important here that the chip and the sink are next to each other, and there's just one chip. Because we can't actually have this action be of the Sandpile group, because then it's not well defined what happens after you contract E. If you contract an edge, suddenly the Sandpile group changes what is going on. So this was very difficult to come up with, but it turns out that this is always going to happen as we get this, this commuting diagram in this specific instance where we have this edge that is in both the starting spanning tree and the final one. And some people might be able to guess what's going to happen next is we get sort of the dual picture with deletions. So if we choose an edge that's not in the starting spanning tree or the final spanning tree and we delete it, then what we end up getting is the same final spanning tree, but the graph has now deleted this edge. So I spoiled that a little bit, but hopefully you don't mind. And I chose the sort of simplest non-trivial example where you actually get some interesting stuff going on, where it's not just like, it is easy to show if you don't cross that edge. When you do, it's a little bit trickier to say what happens. And in the interest in time, I think I'm going to skip the last thing. This is just something that tells us we don't really have to worry about cut vertices. It ends up, we're not even positive that it's not implied by the other two, but it ended up being really helpful for us to have this extra thing. So you can look at that on your own if you want to. This ended up taking us 3 cases for each of the first 2. it was tricky, but coming up with this, coming up with a conjecture of this being true was more challenging than proving it itself. It's sort of a medium difficulty type of thing. So we use this definition or this property to define what it would mean to be a consistent Sandpile torsor algorithm. So a Sandpile torsor algorithm is consistent if it satisfies these properties of like you have this contraction, commuting with contraction in this specific case, commuting with deletion in this specific case, and then something about cut vertices that basically goes down and we only have, let's just focus on two connected graphs is kind of the idea. 1 minute, okay. I can get through this pretty quick. So here's the big theorem, is in fact, this is a defining property of rotor routing. It's not just a property of rotor routing. Every consistent Sandpile torsor algorithm is gonna have the same structure. And so to actually prove this was very challenging. This is probably of any proof I've been involved in, this is the one I'm most proud of. It started, we had to find a way of describing rotor routing in general by sort of local moves that would fully describe things. Then we use induction to reduce to 4 special cases. And then it's a nightmare to resolve those 4 special cases. That ended up being a lot of work on its own. And the last thing I'm not going to get into is I think that the right generalization is to regular matroids. And I can make all the statements in regular matroid land. I'm just still working on proving these. And we basically have the same conjecture of this putting things in regular matroid land, this algorithm that's known, is it consistent and is it the unique consistent one? I think I pretty much have a proof of the first part, but the second one could be challenging because it was very challenging in the graph case. And that's it. Thank you for listening. Here's a crazy graph that we had to use for one of our cases.
Do we have any more questions for Alex?
Just before the Sandpile matrix tree theorem, I noticed the definition of Laplacian matrix. I'm wondering, what is the significance of the matrix there just before the matrix tree theorem?
Yeah, that's a good question. That's something that I definitely sped way too quickly through because I wanted to give sort of the easiest to define definition of the Sandpile group. But the idea is this Laplacian matrix has the stuff on the diagonal is the degree of your vertex. And then the stuff on the off diagonal is -1 if there's a connection between the two vertices and 0 otherwise. So what you can realize is that doing a firing move is exactly adding some row of this Laplacian matrix. In particular, you add the row associated with V, or actually you should really subtract the row associated with V, because then you subtract degree many chips from that vertex and you add it to the other one. So there's a way of describing this purely algebraically, but I kind of like the dynamical perspective because it gives you a nice way to think about it.
Okay, thank you. More questions?
In the deletion condition, if the edge that you delete is actually in the final spanning tree, what happens then? Because you can't.
So you're not allowed to do that. We're always contracting edges that are in the spanning tree or deleting edges that are not in the spanning tree. So there's a lot of restrictions to what we are actually, the situation where we could actually get this sort of consistency. So it was really exciting when we found that it was enough to be a defining property for rotor routing. But yeah, you only delete the stuff not in the tree, you contract the stuff that is in the tree.
So, more questions? So you mentioned at the end the this case analysis. That seems that's very tedious. Do you think there's a way of getting rid of this case analysis?
I'm scared to make too much of a guess, but I think that if there was, it would have to be coming from like a higher up perspective. Like maybe there's some deep theorem in matroid theory that you could use to do this. But I think without kind of going higher up and looking from there, I think that it really is necessary. And some of the cases, I mean, there's no way to completely get rid of them because there's situations where clockwise rotor routing looks the same as counterclockwise rotor routing. So you got to figure out exactly when they differentiate from each other. So I really do feel like we found a reasonable proof of this thing. I'm not super disappointed in an ending in case analysis. I think that is kind of the way it had to go.
Okay, thank you. Let's thank Alex again for a very interesting talk.
Thank you, everyone.
And now we have, for us here, we now have a coffee and it's right outside. Okay, and then we reconvene at 11 o'clock. And you at home, you have to get your own coffee.
check, 1, 2, 2. Check, 1, 2, 2, 1. Check, 1, 1. Check, 2, 1. One, one, two, three. One, two. One, one, two. One, one, two, two. One, one, one. Check, 1, 2. Check, 1, 2, 2, 2. Check, check, check. A, A.
ಮತ್ತೆ ಚಾರ್ಜರ್
எதுவுமே நீங்க ஆன் பண்ண வேண்டாம்.
Hey, hey. Check.
say something to Don? Okay, so. Hi, Don. Svante here. Are you ready?
Yeah. I have a bit of trouble hearing you. There's a lot of echo, but otherwise, sure.
Okay. I'll turn this mic off.
Okay, and we welcome everybody back for the next part of this morning session. And now we're going to have 2 online talks. And no, can you share? Okay, we should first. So this is Don Betia, who will give us this talk. He's in Kluvens in Belgium. And so I think, so please, Don, can you share your screen and start your talk?
Yes. Share. I want to go to view and then enter full screen. Oh.
That's also very interesting. Your CV.
Sorry, can you see? I have a. Can you see something? I think I shared the wrong window. Yes. 1 second. Here we go. Now.
That's much better.
Yes. Right. Sorry about that.
There you go. The floor is yours, Don.
All right. Thank you very much. And I want to thank the organizers for, well, I know how much of an effort they put into organizing this, especially in these difficult conditions, doing it online and in person as well. Today, I will talk to you about a simple model of plane partitions, and more precisely of cylindrical plane partitions. And actually, the goal of this talk today, I hope everybody can hear me, by the way. If not, please raise your hand in the chat or if there are issues. The goal of today's talk is to tell you or to try to convince you that complex probabilistic behavior can arise from considering simple combinatorial models, probabilistic combinatorial models that people have considered in algebraic combinatorics and in probability for at least half a century by now. And I'll start with a warm-up. And the warm-up is plane partitions. And more precisely, I'm going to look at trace and volume weighted plane partition. So a plane partition is what you see in the figure. It's a stack of boxes in the corner of a room. It has a volume, the number of boxes, and it also has a trace. It has many other things, but so the trace is the number of cubes in the middle. So if you write the plane partition as a height function, this would be the trace, as in the trace of an actual matrix. The trace is just the number of cubes under the red tops. So it's equal to 12 here. And if you sum over all plane partitions, the partition function, what I call Z, has first been computed by Stanley, I believe, in the late 70s. And it's equal to the formula that you see below, to the nice product that you see below. If I put A equals 1, I just get Q to the volume measure, the most natural measure you can think of. And for the purpose of this talk, I'll always be interested in extremal statistics. So I'll be looking at the height of this guy, at the distribution of this guy under this measure. I can look at other things. I can look at the distribution of this guy. I can look at the distribution of this guy. I can look at joint distributions. That's not important. I'll just focus on this guy. It turns out that using a theorem of Green and various combinatorial correspondence like the Robinson-Shanstad-Knuth and the Birch correspondence, the distribution of this guy, so what I call lambda 1, 1, the distribution of the peak, has many other interpretations. It's equal to both L1 and L2 in distribution. What are L1 and L2? Well, imagine that you have a field and each dot here is a random variable and they're equidistributed by diagonal. So this dot is a geometric random variable of parameter AQ. A geometric random variable is just defined here. It's the simplest object you can think of, probabilistically. These two are geometric random variables with parameter AQ squared. These four are independent geometric random variables with parameter AQ to the fourth, so on and so forth. So they're all integers. And now imagine trying to maximize over all paths like the yellow one, going from 1, 1 all the way to infinity. The maximum of that is what I call L1. Borel-Cantelli tells us it's almost surely finite. Now try to maximize over all paths going from here to here. This is what I call L2. So L2 goes in the perpendicular, L2 goes over paths that go in a perpendicular direction. And this is also equal to gamma 1 in distribution, where gamma 1 is the first part of a partition distributed as such. So this is a nice product, actually. This is a Schur function evaluated at, well, a principal specialization of a Schur function. And all of these are equal in distribution. And our first goal is to figure out what this is asymptotically when Q goes to 1. Otherwise, when the number of boxes here goes to infinity, when the volume goes to infinity. And it's simplest stated, well, the result is a bit, this slide is a bit dense, the result is a bit complicated. But okay, let's unpack it. So L, which is either one of those four random variables, in particular the peak of the plane partition, as Q goes to 1, e to the negative epsilon, epsilon goes to infinity. And in the critical regime, as the parameter of the trace, so remember I was keeping track of the trace here with the parameter A. As A goes to 1 as well, like this, it turns out that any one of those four things fluctuates as twice epsilon inverse log of epsilon inverse. Epsilon inverse is a big parameter. You can call it M if you want. And then it has fluctuations of the order epsilon inverse. So M log M, order of magnitude, and order M fluctuations, where M I just arbitrarily call 1 over epsilon. And the distribution can be written somewhat explicitly and is a so-called Fredholm determinant. So it's a determinant of an operator. That operator is given here. It's this quantity in exponential variables times something. And this quantity, this operator, is called the Bessel operator, and it's actually a universal object in random matrix theory. So there's quite a bit on this slide still. So let me move on a little bit and to tell you why this distribution is nice and interesting. Well, it turns out that this distribution, G alpha, which is a Fredholm determinant of something a bit mysterious, at least in combinatorics, has two nice limits. When alpha goes to infinity, you get the so-called Tracy-Widom GUV distribution, which has the property that it's actually universal in, for example, if you look at the largest eigenvalues of random Hermitian matrices with i.i.d. entries. If you look at alpha goes to 0, G of 0 is the Gumbel distribution, which also turns out to be universal. If you look at the maximum extremal statistics of i.i.d. random variables. So in the second case, you looked at maxima of highly correlated systems, and in the first case, you look at maxima of extremal i.i.d. systems, maxima of i.i.d. systems, i.i.d. random variables. And this alpha somehow goes between the two. So you look at two different universality classes. One is the so-called, I suppose, Gaussian class, and you look at extremal statistics therein. And the other one is the so-called KPZ universality class. I will not talk too much about this. And this is where you see Tracy-Widom. And this simple trace parameter that was first introduced by Stanley, I believe, in the study of plane partitions, kind of goes between the two. I should also say that Bessel itself, if you take the Fredholm determinant of this operator, that is also a universal object in random matrix theory, and it appears when you look at the lowest eigenvalue of random covariance matrices. So take XX star, where X is a random matrix with some entries, some i.i.d. entries. XX star is Hermitian, it's positive definite, its eigenvalues are positive, it has the lowest eigenvalue, which is close to 0. If that matrix is m by n, so this is going to be an m by m matrix, and m minus n is equal to alpha fixed, then you're going to see determinant of 1 minus this operator, as opposed to the same guy in exponential coordinates, universally as n goes to infinity. This is, for example, there are many results along these lines of Tao and Wu and Egdersh and Yao and many people in the random matrix community. All right, so if you take nothing from this talk, and I haven't mentioned our main result yet, if you take nothing else from this talk, what you should take is that very simple models, in our case, combinatorial models of plane partitions, if you look at natural distributions on them, they have this somehow somewhat mysterious but somewhat natural interpolation when you look at statistics, extremal statistics in our case, between two very different types of classes. One is maxima of i.i.d, the other one is maxima of eigenvalues of random matrices. Okay, so I mentioned Fredholm determinants. What are Fredholm determinants? Well, if you have an operator that acts on functions by multiplication, this is on a measure space. This could be a finite matrix, so then it's matrix multiplication. It could be an infinite discrete matrix, or if it could be an infinite continuous matrix, i.e. an operator. Its Fredholm determinant is just this. I think this is called the Sylvester expansion, perhaps. If you do this for a matrix, all of these are going to be finite sums over all minors of the matrix, principal minors. And you can also write it like this. So that's a Fredholm determinant, because this object is going to be appear throughout this talk. This is just a reminder of what Fredholm determinants are. And now let me mention that we can actually go a bit further, and you'll see this when we're gonna talk about the main result, but let me mention it in one slide here. Depending on this trace parameter for plane partitions, so recall again that a to the trace here, so q, in order to see something interesting, you want to let q go to 1. Because otherwise you have finite volume, you're not going to see anything interesting. But you have a freedom of playing with A. And actually, if A is 1, precisely 1, you have Gumbel fluctuations. This has been proven by Velshik and Yakubovich about 15 years ago. If A is less than 1, but fixed, so A doesn't go to 1, this has been, well, you have Tracy-Widom fluctuations. So what you would expect from the main theorem from this limit on a different scale, and we proved this. And the result I showed is this transitional case when A goes to 1 critically. And I should say that that this interpolation was first discovered by Johansson in 2008. And actually, he was looking at a model of last passage percolation similar to this. So he was looking at maximizing paths similar to what I have here, with some differences. You have exponential random variables. You have a finite rectangle instead of an infinite field. There are some differences, of course, but this distribution itself and this interpolation was first discovered by Johansson in the study of polymers, of last passage percolation. All right, and now to the actual main content of this talk. So in this talk, we're going to look at, roughly speaking, the same objects, but now on a cylinder. What do I mean by that? So imagine a plane partition in a corner of a room, but now imagine that you wrap the room, well, it's explained here, you wrap it around and you identify the two vertical sides. So that gives you a cylinder, and this cylinder, for simplicity, has width 2n, twice n, capital N, and here is equal to 3. And so let me call lambda such an object, a cylindric plane partition. Alternatively, you can think of it as a dimer configuration of on a cylinder, because you have plane partitions are equivalent to lozenge tilings. Well, this is obvious in the picture, and lozenges are dimer configurations by simple bijections on the dimer configurations on the hexagonal lattice. And you can look at the cylindrical geometry. And let me tell you the distribution that people want to study in cylindrical geometry. Well, you'd want to study Q to the volume. But as you saw, it's interesting if you actually keep track of the trace as well, and perhaps of other things, but it's certainly interesting if you keep track of the trace. So we want to do the same thing as in the warm-up that I mentioned, except that if you think about it for a second, this doesn't quite make the partition function finite, because when you wrap things on the cylinder, you have this seam, and you kind of have to keep track of it. Otherwise, the partition function, even combinatorially, is not finite. So the seam is just the height, the total height of the things that you see here. The seam is equal to 3, so 2 plus 1. It's also the height of the things here, because these are identified. And how do you keep track of the seam? Ideally, you could do it with well, in principle, you could do it with a different parameter, arbitrary parameter. But things are complicated enough with the number of parameters that we have now, which is A, Q, and the width n, twice n. So let me simplify it a bit and just declare that the seam has this parameter to keep track of it. But again, we can do it with an arbitrary parameter. Things are just nicer if that parameter takes this particular value. So again, I have a trace. I have a 11, the number of things here in the middle, the number of cubes in the middle, a seam 3. And then this weight, if you sum over all plane partitions, has a partition function. So the generating series for such things is known. It's hard to attribute it properly because it goes back a while. So it's in McDonald's book as an exercise. The relevant sum over symmetric functions, Sagan and Stanley give a very nice bijective proof from the 80s. Kratenthaler computes this in the 90s, or maybe early 2000s. No, in the 90s using non-intersecting lattice paths. Borodin has recomputed this in the 2000s, and Jérémy Boutier and I have recomputed this a few years ago using vertex operators. So there are many people have computed this quantity in more or less explicit ways. And I should say that such objects are actually interesting in theoretical physics and in algebraic combinatorics for independent reasons. And for example, if you look at Rojak's Ramanujan identities, there are some recent papers of Cortel and Jean Douce and where they where they use such objects to study various classes of Rogers, Ramanujan, and more general identities. And again, there they kind of look at the peak. Right, so let me give you some equalities in distribution. So again, I'm interested in the peak. I'm interested in the distribution of this guy. Let me give you some equality in distribution. First, lambda 1, 1 is equal to the first part, lambda 1 of a partition, which comes from this two-partition model. What's a two-partition model? Well, this is a Schur function. It's a skew-Schur function. These are partitions. In particular, it means, and I'm looking at a probability on two partitions, lambda and mu. It's a skew-Schur function evaluated in a principal specialization. I have this parameter A as well. The two partitions are correlated here. So there's some interaction between them that's fairly complicated. Mu also appears here. And then I'm looking at lambda 1. So I have this distribution. I trace over everything except lambda 1. Lambda 1, 1 is also equal to capital L plus kappa 1, where kappa 1, first of all, is independent of everything else. And it has this simple distribution. This is an infinite Q Pochhammer symbol. This is a discrete Gumbel distribution. And what's L? L is the longest polymer. So imagine you have a cylinder that looks like this, n is equal to 3 here. And you have these small squares on your cylinder, 1 in the first diagonal, 2 in the second diagonal, and from some point onwards, you only have 4 squares in each diagonal like this, in each horizontal line. And in these small squares, you put independent geometric random variables with parameters that vary according to the diagonal, to the square, to the horizontal line you're in. So here you have a geometric random variable with parameter AQ. And here, for example, every number in every square is a geometric random variable with parameter AQ to the 6th, because we're in the 6th diagonal. And you again look at the longest path the longest path using these two steps, these two sequences of steps, starting from here and going all the way to infinity. And lambda 1, 1 is equal to the length of that in distribution plus something independent. Incidentally, an interesting connection by Imamura, Muchikoni, and Sasamoto from 2021. Well, actually, they didn't prove this, so this is something extra you have to prove from their result. But this L has a nice interpretation. So this L equals in distribution rho 1, where rho 1 is the first part of a Q-Whittaker distributed partition. So there are these polynomials called the Q-Whittaker polynomials, the McDonald polynomials when t is equal to 0. Take them at a principal specialization, put the Q parameter to be Q to the N, capital N. And this L, which comes from a cylindric geometry, is equal to this rho 1.
Please try to wrap up now, Don.
Sorry about this. We started a bit late, it's true. Okay, so let me tell you the main result. And the main result is, it has 2 parts. And the width of the cylinder is fixed and A grows critically, A goes to 1 critically. Then lambda 1 is the peak. They're the same in distribution. Grows as m log m with order m fluctuations. And you get this Bessel kernel in exponential coordinates and in finite temperature. I should explain what that means in a second. When when epsilon goes to 0. There's a second regime when n grows slowly, but a is fixed, n grows like this, and then lambda 1 grows differently, order epsilon inverse, with fluctuations epsilon to the -1/3, and you get a different distribution in the limit, which is this Tracy-Widom distribution in finite temperature. So it's a Fredholm determinant of this kernel. And the Tracy-Widom distribution in finite temperature is yet another distribution, somewhat universal, that interpolates between Gumbel and Tracy-Widom as the temperature parameter goes to infinity or 0. And this Tracy-Widom distribution appears in models of continuous fermions and matrix models. It appears in the KPZ equation, the Kagdar-Parisi-Zhang equation, and there are many works on this. And our systems, first with Jeremy Boutier, but of which I haven't talked about, and this one with Alessandra Ocelli, actually kind of makes a bridge between these two, between these models of random matrix models and between the KPZ equation, based on what I told you here. There are many other things you can do. As n goes to infinity, you recover, in part 1, you recover the Bessel kernel that I told you about before, which already interpolates between Gumbel and Tracy-Widom. In part 2, you interpolate between Gumbel and Tracy-Widom via this finite temperature thing. And all of these are there are many other limiting regimes, even interesting ones that one can do. And all of these things are discrete combinatorial models that correspond to systems that people have studied before in physics, continuous systems that people have studied in theoretical physics. Ledusal, Majumdar, and Sher come to mind, and collaborators. All right, I will skip the proof, and I will thank you for your attention. Thank you very much, and apologies for the slight delay.
Okay, thank you very much, Don, for this talk. Do we have some questions from the audience here or from the viewers online? So if you're online, you could raise your hand or write in the chat. I guess I don't see if someone raises their hands, so maybe better if you write in the chat if you have a question. So I have a question then, Don. So you're talking about these cylindrical plane partitions when you wrap the partition around and you need to keep track of this seam, but then this seam has a very special property that people think descends from it in both directions. So could you glue several plane partitions together instead and have several different seams?
So you can so what you're sort of saying, if I'm not mistaken, is that I only looked at things that go up here and then go down here, like a profile where the plane partition increases and then decreases. But you can look at things that go up and down and then go up again and down, and then you wrap it at the very end. So you can certainly do that. Then you would have two peaks, and you can study that. We just chose the simplest model because this was already unknown. And but you can do what you suggested, if I understand your question correctly.
Okay, thank you.
And as long as the profile has, so as long as you glue two things that are going to be macroscopically separated, in the end, the end result is not going to change much.
Okay, I see. That's interesting. Okay,
so if you do things with different profiles, then you get into there's a whole zoo of things you can get into depending on the profile you use for here.
Okay, let's thank Don again for this talk. And then we'll move seamlessly into the next talk by Sui Hong-chan.
Yes, thanks. Can everyone hear me?
Yes, we can hear you. Now we just want to see you as well.
Okay. Can you see me?
We need to remove the pin.
Okay.
Here in our and find you also. Oh, there we have you.
Okay, so can everybody see the
now we can see you.
Okay, that's good.
Okay, so thank you. So now we have Sui Hong Chan, who will talk about some log concave inequalities for posets or a combinatorial atlas even. Okay, please.
Yes, thank you very much for the introduction. And first, I would like to thank the organizers for organizing this conference during this very difficult time. And also, I would like to thank all of the participants for coming also during this difficult time. And the main character for today's talk is the log concave inequalities. And here is how it's defined. So let's say that we have a sequence A1, A2, A3 up to AN. And let's just say that all of these numbers are positive real numbers, just to make things simpler. And we say that this sequence is log concave if for any k between 1 to n minus 1, the square of the kth number, so this number here, is greater or equal to the product of the k plus 1 number and k minus 1 number. So for example, this sequence down here below is a log concave sequence. And one way to check it is that, for example, if I take the number 9 here, 9 squared is 81. 81 is greater than 4 times 15, which is 60. And you can do the same for the rest of the sequence, and all of these inequalities will stay true. So this sequence is log concave. And one reason why log concave inequality is useful or important is because, in particular, log concavity implies unimodality. So this means that the sequence will first increases up to a certain point at this top, decreases afterwards until it disappears. Just like how we hope that COVID numbers would have been in an ideal world. Of course, the COVID number is not unimodal, but anyway. Okay. So the quintessential example of the log concave sequence is the binomial coefficients. Here, n is fixed and k is changing from 0, 1 up to n. And ak, so the number in your sequence, is the binomial coefficient n choose k. And for this, so this sequence we know is log concave because, well, we can just do direct computation. If we compute this ratio, ak squared divided by ak plus 1 times ak minus 1, this thing is equal, after some calculation, to 1 plus 1 over k times 1 plus 1 over n minus k. And because our k is between 0 and n, this number is always greater than 1. Okay. And just a little bit of spoiler here, but in the few couple of slides, these numbers 1 plus 1 over k times 1 plus 1 over n minus k will appear again. So it might be a good idea to keep them at the back of our mind. Okay. So the second example for log concavity comes from permutation, where ak here is a number of permutations of n elements with exactly k inversions, where inversion of a permutation is a pair of I and j, such that I is less than j, but pi I is greater than pi j. Okay. And this sequence is log concave. And unfortunately, or maybe fortunately, we cannot actually use direct computation anymore, because there's simply no, as far as I know, there's no closed form formula for AK. Instead, what people usually do is that they first write a generating function for this sequence. This is also or the formal power series to fix with the this conference Fpsac. And when you look at this formal power series, you realize that, oh, what a coincidence! This power series is a product of polynomials, and each of these polynomial, the coefficients, form a log concave sequence. And it turns out that this property of coefficients forming a log concave sequence is preserved under product of polynomials. And that is how we know that the original sequence is log concave. Up till here, are there any questions about definition of log concavity? Does everybody think that log concavity is a friend? Okay, I see no questions, so I presume everything is good. So let me continue. So in general, if somebody hand you an arbitrary sequence, there's no reason to expect that this sequence will be unimodal, let alone log concave. So that's why if you somehow have a combinatorial sequence and you keep seeing that it is log concave, then usually the log concavity there is there for a reason. For the binomial coefficient, let's say that is by direct computation. For the permutations, we see that it's there because log concavity is preserved under polynomial products. And today, our goal is to discover yet another reason for log concavity. And this time, this is the reason why we see so many log concavity for matroids. Okay? That is our goal for today. So I believe that many of you already know matroid, but let us just do a quick review so that we all have the same notation, have the same understanding. So a matroid is an abstract set system. It consists of two inputs. The first one is the ground set, which is denoted by X. And for today's talk, we just assume that X is a finite set. The second input is I. This is the independent sets. This is a collection of subsets of the ground set. And they need to satisfy two properties. The properties, I will explain in the next slide. But before that, let us just look at two examples, just to make sure that we have a concrete example in our mind. Okay, so that this thing is not very abstract. The first one is called the graphical matroid, where the ground set X, this is simply the set of edges of a graph G, of a given graph G. So, and G here is a finite graph. And independent set, a set is independent simply if it's a set of edges such that they form a forest in the graph. So there's no cycle. So that is one example. The second example is called the realizable matroid, where the ground set is any finite set of vectors over a field F. The field F here can be finite, can be infinite. And in fact, soon we will see some examples with a finite field. And the independent set here is, pardon the pun, is a set of vectors that are all linearly independent to each other. In fact, this is actually the reason why this thing is called independent set in the first place. Okay. And so here is two conditions that matroid, the independent sets need to satisfy. The first one is called the hereditary property. So this says that if you have two subsets, S and T, and one of them is contained in the other one, okay? And the larger set, let's say T, is independent. Then the smaller set is also independent. For example, this collection of edges has two edges. They don't have forests, they don't have cycles. So this is a forest. Now, if I delete any one of the edges, let's say I delete these blue edges, the resulting set, which is called S, is again independent. It's again a forest, right? Because when you delete the edges, you do not, if you don't have cycles in the beginning, you will never form a cycle at the end. Okay. The second property is called the exchange property. This says that suppose that you have two independent sets, and one is smaller than the other. For example, in this, the set S here, the one with red edges, has one edges. The set T has two blue edges. So one is less than two. So S has less element than T. In this situation, you can always find an element from the larger set, which is this blue. There's these blue edges. You can find one of the blue edges. Let's say these blue edges. Move it to the smaller set, and the resulting set is again independent. It's again a forest. That is what is called the exchange property. So these two properties are arguably, you can say that it's quite abstract, but it turns out that these two properties are sufficient to get log concavity for matroid. In fact, in one of our sequel work, we showed that in some sense, these two properties are also necessary if you want to get log concavity for matroid. Okay. In any case, let me go to any questions so far about the definition of matroids? No questions, so let me continue. Okay, so there are many conjectures about log concavity for matroid, but today let me focus only on one of them, the Mason's conjecture. So 50 years ago, Mason looked at this number ik, where he said that, oh, let ik be the number of independent sets of size k. In the case of graph, this is the number of forests with exactly k edges. And Mason computed many examples, and he believes that, seems like this sequence I1, I2, I3 up to In is log concave. But now, Mason is a very ambitious person. He thinks that, okay, we cannot prove that this is log concave. But you know what? Let us go for something even bigger first. How about if I add a constant 1 plus 1 of 1 over k into this equation? Maybe this is still true. In fact, why stop there? Let us get even more ambitious. Let us add another even one more constant, 1 plus 1 over n minus k, into the right side. And this last inequality is known as the strongest form of the Mason's conjecture. And at this point, some of you might have questioned, but maybe you're just too shy to ask it, is that, Sui Hong, why is it that Mason chooses his constant 1 plus 1 over k times 1 plus 1 over n minus k? What is so special about this constant? Well, this is because many of you might still remember that this number is the ratio of binomial coefficients. So this means that even after you rescale this number ik by this binomial coefficient, then this sequence is still log concave. And notice that by rescaling this by binomial coefficient, this number here now has a probabilistic meaning. That this number is a probability that if you get a random subset of size k, that this subset is actually independent. Okay. And the reason why Mason believes that this conjecture might be true is that because he makes the following observation. Okay, suppose that all subset of our matroid is such that suppose that my matroid is such that every subset with k plus 1 element is independent. Then in that situation, all these three numbers are actually equal to 1, and then you achieve equality. So this means that if this conjecture is true, which we now know is true, then that means that this inequality is tight, that there is nothing we can do to improve. Well, that's actually not the case. So actually, at the end of this talk, we'll show that there's actually a way to slightly improve this inequality. But before I do that, before we go through that, are there any questions? Okay. Feel free to ask questions now. I think it's a good point to ask questions. Okay. If there are no questions, then let me go to the very brief history of the Mason's conjecture. How we solve the Mason conjecture as a humanity. So the first big breakthrough was made in 2015. So the 2018 here is the journal publication date by Adipasito, Her, and Katch, where they show that yes, this sequence is log concave, and they do it in a very beautiful way by using ideas from algebraic geometry called Hodge theory, and they convert it so that it can be applied to the matroid. Okay. This idea was pushed further in the work by Her, Rotor, and Wang in 2018, where they proved the second Mason's conjecture. And the idea here is that rather than working directly with this number ik's, they work with this other object that's called the correlation inequality and apply the Hodge theory. And at the end of the day, after the dust settles down, this constant 1 plus 1 over k magically falls out of the calculation. Okay. And finally, in 2018, 2020 is again the publication date. It was shown independently by Anari, Liu, Oves, Garan, and Vincent. And I think in particular, Cynthia will talk, I presume we'll talk about this more tomorrow. And also by Brendan and Her, where they show that, yes, the strongest form of the Mason conjecture is also true. And the way they do this is a bit different than the previous two. For this one, they instead develop a new theory of polynomials, where the Anari's group call it strong log concave polynomials, while Brendan Her's group call it the Lagrangian polynomials. In particular, these three works were cited by the International Mathematical Union as part of the reason to award the Fields Medal just 2 weeks ago to Junhe. Okay. And just last year, this work was pushed a little bit further by Murai, Nagok, and Yazawa, where they show that the equality can occur in this Mason's tree if and only if every subset with k+1 elements are independent. So notice that the if condition has already been known by Mason since 50 years ago, but it's only now that the only if condition is known, that we now know that these are the only equality cases. For all other cases, this inequality is tight. So this is a very short, very simplified history of the Mason's conjecture. Of course, there are still many other amazing works by many other amazing authors. Some of them are actually in the audience today. And that's why I sincerely apologize that I cannot cover all of them in this talk. And before I proceed further, are there any questions? Okay, if there are no questions, then let me continue. So, okay, in fact, let me go back a little bit to the Mason 1 and Mason 3. And I want to look at the evolution of ideas in the proof of Mason's conjecture. So we see that for Mason 1 and Mason 2, we, as in humanity, uses the ideas from algebraic geometry to solve problems in combinatorics. This is a very good idea, of course. You know, algebraic geometry is very beautiful, very useful, but they can also be a little bit rigid. And that is why we see that in Mason 3, rather than using Hodge theory, instead a polynomial theory was introduced to make things a little bit more flexible so that it can prove a little bit more. And today, our goal, our philosophy, is to push this philosophy, to push this idea as far as possible. We want to develop a new tool that is as combinatorial, as simple as possible, so that it can be more flexible, can prove a little bit more. And the result of doing that is this new method that we call the combinatorial atlas, where this method can be used to prove log concave inequalities. And by using this method, we managed to reprove log concave inequalities that is known for matroids, morphism of matroids, and Stanis-Poisson inequality. And in all these three cases, we actually refine them. We actually prove a stronger form of the inequality. And in other topics, such as the discrete polymatroids, Poisson antimatroids, Ransing gradoids, and interval gradoids, we prove completely new log concave inequality. Okay. Not only that, this method also comes with a built-in tool to systematically find out the if and only if conditions for equality. So this is very useful because the equality conditions are usually used as a benchmark to show that we have a have a better understanding on the combinatorial structure. Okay. And of course, there are in this list of 7 things. There's no way I can cover all of them. So I hope everybody can forgive me for today if I only cover for the first one. Okay. But before I do that, are there any questions about what we want to do? Is everything clear so far? Okay. Okay, if that is happy, then let me continue. So let me today only show our application for the matroid to show you how we refine the inequality to something stronger. And unfortunately, the refinement for the general case of my all matroid is a little bit complicated to state. So let me do a warm-up case first for the case of graph. And in this case, let G be a simple connected graph and let K be the number of vertices minus 2. In this case, we can improve the Mason tree from the constant 1 + 1 over n minus k to this new constant of 3 over 2. And not only that, we can also derive the equality cases where we know that equality occurs if and only if that G is a cycle graph. So that means it's a triangle, a square, a pentagon, a hexagon, and so on. And I claim that this new inequality is numerically better than Mason tree, because we can show that this constant 3/2 is always greater than or equal to 1 + 1 over n minus k. Not only that, I also claim that this inequality is asymptotically stronger in the following sense. So now suppose that you take the number of edges of number of vertices, suppose that this number goes to infinity. So in the language of algebraic geometry, this means that I take the genus of the graph, the genus of the manifold to infinity. In this scenario, our inequality gives 3/2 as a lower bound for this ratio, where the Mason tree can only give 1 as a lower bound. This is what I mean by that the bound is better numerically and asymptotically. Okay. Okay, if everybody is happy with this with the case for graph, let me now show you our first main result, which is our refinement for all metrics, not just for graphs. And our refinement is as follows. In Mason tree, we replace the constant n minus k with a new constant that we call the parallel number, and this number depends on 2 parameters. The first one is that it of course depends on k, and the second one is that it depends on the combinatorial data of the metric. Okay. And I will define this in the next slide. What is this parallel number? But before that, let me just show you some examples, just so that we have an idea what is this parallel number. First, suppose that you have no combinatorial information at all. You don't know anything about the metroid. You just know that it is a metroid. Then the best we can do is the same as what Mason has done. What Mason has predicted. That n minus k is the best we can say. However, if we just know a little bit of a metroid, let's say that, I know that this metroid is graphical metroid. Then in this case, you can get the improvement to 3/2 that we saw in the previous slides. And this improvement depends on your metroid. Sometimes it's a big improvement, sometimes it's a small improvement. For example, if you look at realizable metroids over a finite field FQ, then the constant parallel number becomes this constant over here. The exact formula is not very important. The important thing here is that as Q goes to infinity, this number roughly converges to 1 + 1 over n minus k. So this means that this is not a big improvement compared to the original Mason. However, in some other scenario, such as for the Steiner system metroid, which let me not define just to save time. In this case, this constant asymptotically actually goes to infinity when you take n and k goes to infinity. So for this particular family of metroid, our improvement is actually very big. But regardless, whether the improvement is big or small, I claim that this is always an improvement because we can show that this parallel number is always bounded from above by this n minus k + 1. Okay, and therefore this is the improvement. Up till here, are there any questions except for the definition of the parallel number?
Yes, there's questions. Do you hear me?
Yes, I can hear you. Please feel free to ask the question.
Can you go back to the very first statement of the improvement?
Yes.
Because when you say that k is equal to the number of vertices minus 2.
This one, yes.
So what I don't understand here is the k the same as the index of the independent set?
Yes, this is the same as the index of independent set. And that's actually a very good question because we actually have the other improvement also for other values of k. It's just that the number is not as nice as not as easy to write as 3/2. So that's why for this one we only put for this number. Yes.
Yeah, but that means that you don't have a family of inequalities in that case, right?
So this is so in this case it's for graphical metroid for any graph, and when the value of k is number over this minus 2. For other value of k, we have other numbers for this 3/2.
Okay.
Yes. Just that I just choose this one because it's the easiest one to write. Yes. Thank you for the good question.
So try to finish in 2 minutes now. Sweet.
Okay. In this situation, let me just skip the definition of parallel number, and let me show you the second main result, which is the equality cases, right? Because that's what I promised, that we can do equality cases. And so unlike for the Mason tree, where the equality case is basically one sentence, here we have a much bigger diversity when it comes to equality cases, because we just as can be seen from this slide. So, for example, when the parallel number is the largest possible, then the equality cases is the one that the Mason has predicted, which is when every k plus one subset is dependent. On the other hand, when your parallel number is the smallest possible, then we also have equality cases that we have seen from our previous examples, which is for the graphical matroid when the graph G is a cycle. Somewhere in between, when the parallel number is between these 3 and n minus k plus 1, we have the equality cases for the realizable matroids when the matroid contains every vector of dimension n. And there's also another equality cases for the Steiner system matroid, but let me not talk about them to save time. But the takeaway of this slide is the fact that unlike in the previous case, unlike in the Mason tree, here we have many more equality cases. And all of them, at least from the first glance, look very different. However, I claim that despite all of this difference, despite all of this diversity, we can actually unify them. We can actually explain them in one sentence. Okay, one sentence to rule them all, one sentence to unify them, which is our second main result, the if and only if conditions for equality. And of course, even if you look at this directly, it might look a little bit complicated. But I like to think about this in terms of the isoparametric inequality, which is the inequality in geometry, which says that if you have Euclidean object where the volume is fixed, then the surface area is maximized by the Euclidean ball, which is the Euclidean object such that which is at the Euclidean object that is as symmetric as possible. That when you look at all angles, it all look the same. And it turns out that to say something is as symmetric as possible for the for matroid is the same as saying that first, if you basically this description that if you contract the matroid by any independent set of size k minus 1, all of this contracted matroid has the same number of parallel classes. This thing I have not defined, but it's just you can think of this as the codimension 1 faces of the matroid. And the conditions say that all of the codimension 1 faces are the same. And the second one, which is basically saying that all codimension 2 faces are the same. And it turns out that these two conditions on the codimension face and codimension 2 faces are the equality conditions. Once it's achieved, this is that you actually achieve equality. Okay. And let me conclude today by just mentioning that for today I only mentioned the result for matroid, but our method actually is actually a very general method. It can be in our paper we actually use the same method to prove new like 7 new actually maybe like 14 inequalities for 7 different topics, which I list over here. And we stop at this 7 because at some point we realized that if we keep going, the paper will become 200 pages, not 70 pages. That's why we stopped there. And actually, even after that, we realized that even 71 pages paper is a bit scary. That's why after that, we wrote another paper, which is the expository version of the paper, that is 28 pages. The tools there is a little bit weaker, but still enough to prove Mason tree. It's not enough to prove the refined inequality. But but because of this, the proof also becomes much more simpler and become much easier to understand. So my suggestion is that if you want to start reading this topic, I would suggest to read the 28 pages paper first. And if you are still if you want to learn more, go for the 71 pages paper.
Okay, thank you, Sui Hong Chan, for your talk. So do we have some question for Sui Hong Chan?
Hi, I'm curious how your method compares to the like combinatorial Hodge theory method. Is it similar? Is it completely different? Are there situations where the Hodge theory one is stronger? I just am curious about that.
That's a good question. So the question is about the comparison between the Hodge theory and our method. And as far as I know, they are pretty different. So there's of course some similarities. In particular, we both actually use the fact that we are use this thing that is called the hyperbolic inequality. So that is the underlying theme. But I think that's as far, I think in terms of similarity, that's as far as it goes. So other things are actually pretty different.
More questions?
So is it then that you merge the ideas of Hodge theory and Lorentzian polynomials?
That is a good question. So I would say that for us actually we do things from the other direction. So the Lorentzian polynomial and Hodge theory, I would say that both of them comes from the Hodge theory. While our direction will actually come from the Alexandrov-Funchal inequality from geometry. So our inspiration is this. So Alexandrov-Funchal inequality is proved by Alexandrov in 1930s, but there's a recent proof by Yair, the Sandpile and Van Handel, that give a more linear algebraic interpretation, and that is actually their work is I would say that we are inspired more from that direction. And in particular, because of doing that, one thing that can be achieved from this that I don't know if can be done by the Lorentzian polynomial, is that it allows us to do things on directed version of many of these results. That is actually why we can achieve this on interval gridoids. Because in a way, gridoid, you can think of it as the directed version of matroid, or directed version generalization.
Okay, thank you. Let's thank Swing Shang again.
Thank you.
So this is the end of the morning session, and before you get to go to lunch, we have an announcement from your organizer.
Thank you. So a few announcements. People who were not able to pay online because of our glitchy system and have promised to pay on arrival, please do pay today. To the secretarial staff outside. If you don't have rupees, we can arrange foreign exchange. You let me know and I'll call. There's a door-to-door service available apparently, and we have already utilized their services. So please let me know. For those who want to post their posters, thumbtacks are available also at the desk. So please feel free to use them. Indian participants as well as invited speakers need to fill the travel forms. Please collect them again from the same desk. Christian has kindly posted the extended abstracts of this conference, a preliminary version on the SLC website, and a link is available on the Fpsac web page, so you can access that. I forgot to mention, if you do not, sorry. Yes, in the schedule tab. So when you go to the schedule tab, you will be able to find the link to the extended abstracts. The Wi-Fi, if you do not have EduRoam, this is the Wi-Fi login password. This is accessible in most buildings on campus. We are going to have the group photo now, at least one group photo right outside in front of the landmark statue of Tata, who was J.N. Tata, who was one of the founders of this institute.
Hello. Could someone confirm that I'm in the correct room now, right now? Hello?
Hi, Piotr, can you hear us?
Hi. Yes.
Okay, great. We're just about to start the session. Just one quick announcement. Where is Shivani? Oh, she's not here. So Shivani is there. So those of you who are interested in the weekend trip to Hampi, please contact Shivani. Okay? Raise your hands. Yeah, so that's Shivani. Okay? All right. So I'll hand over to Professor Raghavan, who is the chair of the next session.
Good afternoon. Welcome back. Welcome to all of you once again from all of us Indian hosts to this conference and also to the one next week in Chennai, where I'm from. Our first speaker this afternoon is Professor Piotr Sniady from the Institute of Mathematics of the Polish Academy of Sciences. And Piotr explicitly wanted a very short introduction. And so I hand over the floor directly to Piotr. So it's yours.
Thank you very much. Welcome to the Museum of Visual Art. I should explain that ART is an acronym for Asymptotic Representation Theory. My name is Piotr Sniady, and I will be your guide today. In this museum, we collect all items related to asymptotic representation theory, which are of exceptional visual beauty. For today's sightseeing tour, I selected two artifacts, two exhibits, chosen specifically for this algebraic combinatorial audience. All right, this means that this talk will consist of two parts, which are roughly independent. Let's come to the first exhibition hall. I will start by presenting in 4 easy steps how can you reproduce this picture on your computer. We start with a fixed Young diagram Xi, and in order to keep discussion focused today, Xi will always be this Young diagram having 4 boxes and having an L shape. For a positive integer s, I consider a scaling of this Young diagram, which means that simply I replace each box of Xi by a grid s times s of boxes. In this way, I get a red Young diagram lambda, which will be the key object for the next steps. I should also mention that sometimes it's also convenient to consider scaling factors s, which are not integers, but are just positive real numbers. If you apply such a scaling, the outcome is no longer a Young diagram. It's no longer a partition, but it still makes sense as a nice geometric object on the plane. The best scaling you can choose for such object is the one is given by the inverse of the square root of the number of boxes. In this way, the resulting object has unit area, and I will call it the asymptotic shape of lambda. It's very useful if you want to compare Young diagrams having different number of boxes. At the end of the day, the scaling factor s will tend to infinity, will become bigger and bigger. All right, so this is this red Young diagram obtained by scaling Xi. And in the next step, I fill this diagram with numbers so that they form a standard Young tableau having this specific shape. Of course, there are many such tableaus, and I choose one at random, such a way that each tableau has equal probability. This is the object which I want to visualize. You can think about numbers in this tableau as information about the elevation, about the sea level of some parts of the ground. The best way to visualize such a geographic type of information is by using level curves. Let us fix a real number alpha between 0 and 1. In this example, alpha is equal to half. By n, I denote the number of boxes of my Young diagram. And by m, I denote an integer, which is roughly equal to alpha times n. Mu is a blue Young diagram, which consists of these boxes of my tableau, which are at most alpha times n. This is a random Young diagram. It's random because the tableau was random. It's a random Young diagram with m boxes. This description of the Young diagram mu is very combinatorial. However, the nice thing is that there is also a purely representation theoretic interpretation for this random diagram. Namely, we start with an irreducible representation corresponding to lambda, with the Specht module V lambda. It's a representation of Sn. I restrict it to a subgroup Sm. Now it becomes a reducible representation. It consists of lots of copies corresponding to various Young diagrams. And now there's a canonical procedure of choosing a random irreducible component from such a reducible representation. It turns out that these two descriptions, the one with sampling tableau and the one from representation theory, give the same distribution. All right, so I just told you how to create a level curve for my tableau. And in the final step, we simply should combine these level curves for various values of alpha. In this example, I have chosen alpha equal to 0.1, 0.2, up to 0.9. This construction is very analogous to the one which we use in cartography when you want to show the elevation of some part of the ground using elevation zones and colors. This simulation was performed for a Young diagram lambda having 10,000 of boxes. If you'd have a bigger computer, you could get a similar picture, and you would notice that as the scaling factor s tends to infinity, these zigzag lines which separate numbers below certain threshold and above become, after certain rescaling, more and more smooth. A probabilist would tell you that we encounter some kind of law of large numbers. As our object becomes bigger and bigger, it seems to converge towards a family of very smooth, nice lines. Can we explain this phenomenon? I will use the following notation. By k in square brackets, I denote a cycle of length k, which means that it's a permutation, permuting numbers 1, 2, 3 up to k. This permutation clearly might have a lot of fixed points. I will also use a blue object. This blue object sometimes called the character ratio. This is the ratio of the usual character of the symmetry group and the dimension of the representation. We are working in an asymptotic setting, which means that we are not having a single representation of a single group. We have a whole sequence of representations. This means that we have a sequence W1, W2. The mth representation is a representation of the symmetry group Sm. All right, so we have the mth character ratio, the character which corresponds to the mth representation, and to the mth representation, we can also associate a green object. This is a random Young diagram having m objects divided as the random irreducible component of our mth representation. All right, So the explanation for this phenomenon, why limit curves exist, why we have a nice picture in the limit, lies in the following result, or I should better say as collection of results, which are due to Philippe Bian. These results roughly say that there's a close relationship between the green objects and the blue objects. The green objects concern asymptotic shapes of random Young diagrams, so which means that we are studying the mth random Young diagram rescaled in the proper way. So this is the asymptotic shape of lambda m. So the green condition is about convergence of these rescaled random Young diagrams towards some limit. I will denote this limiting generalized Young diagram by capital lambda, while the blue objects are of different nature. The blue objects concern the characters. So typical version of a blue result says that we concentrate on the character ratio evaluated on a fixed cycle. So we fix the length of this cycle. We go with the size of the group to infinity, and we study this character ratio after some factor which takes into account that typically such characters converge to 0. All right, so this result of Philippe Bian says that if you, for example, that if you have information about limit behavior of Young diagrams, that they converge towards some limit, lambda, then this specific form of the characters converges to a certain limit. And furthermore, this limit is a nice continuous function of the limit shape capital lambda. This result, among others, says that if you would modify the Young diagrams which you encounter here, like remove 1% of boxes from one part of your Young diagram to another part of the Young diagram, clearly this would change your characters, but this result says that it would not change these characters too much. So there's an interesting continuity behavior around it. This result essentially explains why the limit curves exist. It's a small exercise. You have to apply these results twice for two cleverly chosen sequences of representations. If you look on the extended versions of these slides, you can see the details. I think that for this audience, algebraic combinatorialists, the really important question is, what is sitting behind this result of Philippe Bian? Can we understand better the relationship between the shape and the character, between the green and the blue? There are clearly some classical tools for understanding this relationship between the shape and the characters, such as the Murnaga-Nakayama rule. Unfortunately, this formula, the Murnaga-Nakayama rule, has a number of summands which grows really fast with the size of the Young diagram. So even if you want to study your character on a specific conjugacy class, on a cycle of length k, the number of summands grows super fast, and it's difficult to control their growth. This means that some classical tools of algebraic combinatorics are not very good for asymptotic problems, and it would be nice to find some alternatives, some better ones. My dream formula for this problem would have only finitely many summands, and the number of summands should not depend on the number of boxes. In this way, we could understand asymptotics of each summand separately. Can we find such a formula for the characters? If you want to pursue such a dream, this means that actually you want to change the philosophy of looking on the characters of symmetry groups. Typically, we think about the characters in the following way. We fix the irreducible representation, we fix the Young diagram, and we view the character as a function on the conjugacy classes. These asymptotic problems ask you to do roughly the opposite. We should fix the conjugacy class. For example, you can look on the conjugacy class of a cycle of length k. And now view the character as a functional set of all Young diagrams, no matter if they have a small or big number of boxes. This viewpoint is often referred to as the dual viewpoint on the characters. In order for this approach to be successful, you need to normalize characters in the right way, and it turns out that this definition is the most convenient one. As you can see, I'm fixing the length of the cycle. This is this number, integer k, and what I'm studying is this the character ratio evaluated on this specific conjugacy class. There's also a normalization factor, which is roughly related to the number of boxes on the Young diagram and the conjugacy class. If you look for the first time on this specific normalization, you might not be convinced that this is the best way to do. However, it turns out that with this choice, you get a very nice and beautiful result, namely, if you fix the length of the cycle, if you fix k, and you fix the Young diagram lambda, and now we study the character defined in this way, the normalized character, evaluated on the Young diagram, scaled by the factor s. And it turns out that with this definition, the character becomes a function of s, which is a polynomial of a degree which we control. This is a very nice property, and informally, you can say that with this definition, a character on a fixed conjugacy class becomes a kind of a polynomial function on the set of Young diagrams, which is very nice. This polynomial from this bottom of the screen will be quite useful on the next transparency. For each integer k, I define the k plus first free cumulant of a Young diagram as the leading term coefficient of the polynomial I just studied on the previous slide. Another way of saying this is that I'm inflating my Young diagram by a very big scaling factor, and I'm looking on the first order asymptotics of this character. These free cumulants turn out to be very convenient. Firstly, there are very efficient, very computationally efficient algorithms for calculating these characters, for these free cumulants. Each of them provides certain large-scale information about the shape of the Young diagram. For example, the third free cumulant tells you whether your Young diagram is more elevated to the up or if it's more shifted to the right, while the fourth free cumulant tells you whether your Young diagram is more chunky, more compact, or if it's more stretched up and to the right. My personal perspective is that free cumulants give you a super convenient family of parameters which describe the large-scale shape of the Young diagram. All right, these results of Philippe Bian I mentioned before are essentially based on the very rough first-order approximation, which says that the kth character, the character on a cycle from k, is approximately given by appropriate free cumulant. However, it turns out that you can also find exact formulas. These are examples of the formulas I was looking before. These are formulas which have a finite number of terms, and the number of terms do not depend on the number of boxes. These formulas, called Kerr polynomials, express each character on a cycle by a certain polynomial in free cumulants. Quickly after they were introduced, people noticed that their computer-generated coefficients seem to be positive integers, which was quite surprising. And the computational community interpreted this phenomenon as existence of some underlying hidden formula for the characters of the symmetry groups. This formula is now called a Stanley-Ferré character formula for the characters of symmetry groups. This formula was presented several times on this Fpsac conference, and I don't want to show it today because today's talk is not about answers. It's more about looking for good questions. The funny thing about this formula is that it's elementary in the sense that at least one of its proofs would be available to Alfred Young in the 19th century. You might wonder why Alfred Young didn't discover this formula. And my answer for this is that without computer simulations, without some visual viewpoint on these kinds of problems, you do not notice some phenomena and you do not ask certain class of questions. And in this way, you do not notice some, you are not forced to look for algebraic combinatorial tools which are appropriate for algebraic combinatorial, for asymptotic problems. Very good news is that this is not the end of the story of exhibit A. In fact, there are at least 4 open positivity conjectures related to characters of symmetry groups and to some deformations related to Jack characters, to Jack polynomials and McDonald polynomials. If you are interested in this, I encourage you to have a look on slides which on my website, which contain some bibliographic hints. So the good news is that there are open problems which you can attack in the future. Let's have a look on exhibit B. This exhibit B was created by application of the Robinson-Shenstedt-Knut algorithm, which is fundamental for understanding the representation theory of symmetry groups, and in particular for the Littlewood-Richardson rule. All right, so let me recall you briefly how RSK works. RSK is a bijection which takes as an input a finite sequence of length n, and as an output gives a pair of tableaus, P and Q. P, called insertion tableau, is a semi-standard tableau. Q, called recording tableau, is a standard tableau. These tableaus P and Q have the same shape, and they both consist of n boxes. Probably the best way to explain how RSK works is by looking on the induction step of this algorithm. All right, so here you can see an outcome of RSK applied to a certain sequence of length 9. And my plan is to extend this sequence by adding new element, 18. The first rule of RSK says that this number should be inserted into the bottom row, and it should be inserted to the leftmost box, which contains a bigger number. This means that 37 has to relocate and 18 is inserted into the bottom row. The second rule of RSK says that whenever you bump a number, it should be inserted into the next row using the same rule as before. All right, so we should insert 37 to the leftmost box, which contains a number which is bigger. 53 is bumped, and we iterate. At some moment, it must happen that the number which we want to insert is bigger than all entries in this row. Then we simply insert the number 74 into the leftmost empty box. In this way, the sequence of bumpings terminates. We created a new box in the insertion tableau. I promised you that these two tableaus, P and Q, will have the same shape, and currently it's not quite true. We have to repair this by creating a new box in the recording tableau. We insert number 10 because it's the smallest number which was not used. This is because 18 is the 10th number in our sequence. All right, so an important part of this talk will be devoted to the blue boxes on the left-hand side on the insertion tableau. These are the boxes where bumping occurred. They form a bumping root. And we'll study this object later on. All right, so this completes the description of the induction step of RSK. Let's have a look how RSK works in its full glory. We start with the empty word, to which correspond a pair of empty tableaus. We are inserting new numbers, and the tableaus fill up gradually. Oh, now something interesting happens. I like the number 99 very much. I like this number so much that I painted this green, and I will watch what happens to this number 99 inside the insertion tableau. As you can see, sometimes when there's a new number, when there's a new sequence of bumpings, my number 99 moves up, and sometimes it stays in the same place as before. I think the key lesson which we can get from this animation is that the nature of the insertion tableau is quite dynamic. Its entries are constantly changing. The boxes are moving, while the recording tableau on the right-hand side is quite static. Once a number is inserted there, it will stay there forever. All right, so now I can tell you how the exhibit B was created. You probably noticed that I like randomness a lot. So let W1 up to Wn be a sequence of n independent random variables, each with the uniform distribution on the unit interval between 0 and 1. And let S be a real number. S is deterministic, it's fixed. S is a real number between 0 and 1. Firstly, I apply RSK to sequence of W's. So this Pn, this red Pn, is an insertion tableau obtained by applying RSK to the sequence of W's, and lambda n is its shape. On the screen, this shape of lambda is this big red Young diagram. Okay, so maybe so this lambda is this big red Young diagram. When n tends to infinity, the shape of this Young diagram converges to a certain limit. This result is quite analogous to the one of Philippe Bian, which I discussed before. However, this result is much older. In the end of 1970s, independently, Logan and Shep, Wierzch and Kerov studied this specific random Young diagram, and they proved that its boundary converges to a certain limit curve. All right, so this is our red object. Now it's time to tell you about the blue part of our exhibit B. The blue part is the bumping root obtained by inserting a new number, a new deterministic number S, into our big insertion tableau P. All right, so if you would make a much bigger computer simulation than the one I have done today, you would notice that this blue line typically becomes less and less rugged and becomes more smooth. And the question you can ask is there some explanation? What's the shape of this blue line asymptotically? Exhibit B contains the red part, the blue part, and it also contains a super small green part. This green part is so small that you need a magnifying glass. This green part is indicated by this green cross. This green part is just a single box. This is a box which indicates the end of the bumping route. Formally, you can say this green box is a skew diagram, which consists of a single box. This skew diagram can be described by taking a difference of two Young diagrams. One, you apply RSK to the sequence of S's, and with an extra entry S at the very end. And you compare this diagram with the original RSK applied with the just W's by itself. All right, so this green box will play an important role today for understanding the blue part. It turns out that asymptotically, the position of this green box of the end of the bumping route can be described. There's a result which I proved together with Dan Romik, which says that if you scale your picture by my favorite factor, I always divide by square root of the number of boxes. If you rescale your picture, then the position of this end of the bumping route converges in probability to a certain specific point on the Wierzich-Kerov-Logan-Shep limit shape. Well, the fact that it converges to some point on this curve is not super surprising because our green box is on the boundary of the red Young diagram. However, the nice thing about this result is that there's a specific point on this curve. The coordinates of this specific point are given by trigonometric functions. However, these are not the classical sine and cosine functions. These are new trigonometric functions, RSK cosine function and RSK sine functions. So let me explain you how these new trigonometric functions are defined. This is the Logan-Shep Wierzich-Kerov limit curve, which describes this huge Young diagram. And I marked points on this line which correspond to the parameters which form an arithmetic progression. So S is equal to 0, 0.2, 0.4, 0.6, 0.8, and 0. These 5 points split the area below the curve into 5 curvilinear triangles. And the parametrization was chosen in such a way that these 5 triangles have equal areas. In fact, if you were to explain how the usual sine and cosine functions were defined, well, they provide a parametrization of the usual circle on the plane, which has the same property. If you are looking for algebraic combinatorics in this second part of this talk, in exhibit B, then algebraic combinatorics is hidden here in the proof. We use Eustace Murphy element, and we use the key reason why RSK is so interesting. We use the link between RSK and the Littlewood-Richardson rule. All right, so let's have a look. What does this result about the end of the bumping route tell us for exhibit B? This is a very big Young diagram, a bumping route and its end. Okay, so this result is not super impressive. We just can say something about the position of the end of the bumping route. So we know in this trigonometric function, with trigonometric functions, we can say where this bumping route will end for a given S, which we're inserting into the tableau. How about other points along the bumping route? Well, it turns out that what you should do is that you should introduce a polar coordinate system on the plane. However, you shouldn't use the usual trigonometric functions for the polar coordinates. We should use the trigonometric functions which are tailored for RSK. All right, so let's say that a point along the bumping route has polar coordinates r and phi. R is an analog of the distance from the origin, and phi is an analog of the angle from the usual polar coordinates. Well, it turns out that if you apply these polar coordinates, the problem becomes much easier. And I leave it as a small exercise for students for a coffee break to figure out why these two quantities, r and phi, are related by a super easy relationship. In this way, we obtain the equation for the green line. This is the limit shape of a bumping route. In fact, it turns out that this green curve is quite universal, and you can find it also in some other problems related to RSK. However, for this next slide, I need to start a small animation. All right, so this animation tells a story which you almost have seen at the beginning of my discussion of RSK. I had a green number to which I had an emotional attitude. I liked this number very much, and I studied its history in the insertion tableau. This is exactly what is happening here. We are feeding RSK with a lot of random numbers. And at some moment, we are inserting a number which we like very much. As you can see, the Young diagram is growing. In fact, it's growing in the same way as it was predicted by Logan, Shep, Wierzig, and Karov. The outer shape is given asymptotically by this famous curve. However, what can you say about the trajectory of your favorite number? As you can see, it's moving up and it's moving left. This problem was studied by my student, Mikołaj Marciniak, who is in the audience. And he proved that asymptotically, this green box moves along the same curves as the ones which I studied with Dan Romik on the previous slide from the bumping route problems. We should employ more visual viewpoint on this object. When you're looking on this kind of picture, your mind starts wandering, and if you start asking different kinds of questions, you may ask, what is the future of this green box? Will it ever reach the leftmost column? In fact, the answer is positive. Yes, this box will, with probability 1, reach the leftmost column. However, it will take a very long time. For example, the expected waiting time for this box to reach the leftmost column is infinity, which means that if you would like to make some computer experiments and make some Monte Carlo histograms, you might need a very big computer. This problem was solved in a recent preprint with Mikołaj Marciniak and Łukasz Maczarka, who are in the audience. And I recommend this preprint a lot because it has a lot of beautiful pictures. Until now, I was looking on just a single box. I think it's too little. Let's have a look on something more ambitious. This animation shows a time evolution of the small part of an insertion tableau. about 1% of the boxes was painted so that we can easily track their positions. As you can see, these boxes follow the same universal family of curves, which already appeared in this talk. However, if you would follow this visual viewpoint on live, you might start asking different kinds of questions. What can you say about the collective movement of the boxes? What is the best way to scale time so that this flow becomes stationary? As you can see, this visual viewpoint is an unending story. It's a machinery for generating interesting problems. When you are following this Exhibit B part of my talk, you might have a feeling that there's no serious mathematics behind it. And the key motivations were just how to make beautiful pictures and animations. However, there are also some more adult, more serious reasons for studying these problems. And one of them is related to the infinite symmetry group. The infinite symmetry group is the union of finite symmetry groups. It's an infinite symmetry group, which is non-compact, and its representation theory is much wilder, much more nastier than the representation theory of the usual symmetry groups. In particular, some classical notions from the usual representation theory don't work that nice in this context, and they have to be replaced. We need to consider representations on Hilbert spaces. The notion of irreducibility has to be replaced by more subtle notions coming from the theory of operator algebras, phenomenon algebras. This is a subtle topic. The good news is that in some aspects, this representation theory of S infinity is easier than the usual representation theory of finite symmetry groups. This lies in the result of Wierzcik and Kerov from 1980s, who discovered that there is an intimate link between these fundamental so-called factorial representations of S infinity and certain random infinite tableaus generated by RSK. On the next transparency, I would like to show you how this construction of Wierzcik and Kerov works for a single example. This example is at the same time the most natural and also the most difficult. And I hope this gives you a flavor of what kinds of objects we are working on. All right, so we need an infinite version of RSK. The starting point is a probability space omega, which consists of infinite sequences, W1, W2, and so on. These entries are all selected from the unit interval between 0 and 1. This product of intervals, this infinite product of intervals, is equipped with a probability measure, the product of Lebesgue measures. In this way, you can think about the W's as a sequence of independent random variables with the same distribution, the uniform distribution on the unit interval between 0 and 1. This omega is a very simple probability space. Now I should tell you about the infinite version of RSK. And the bad news is that the insertion tableau doesn't really make sense if you want to apply RSK to an infinite sequence. The reason is that the insertion tableau is too dynamic. The boxes constantly change, and the entry, no part of the insertion tableau converge in some nice way towards some limit objects. So the only thing which makes sense is the recording tableau. Oh, this is nice. Recording tableau is static. once an entry is inserted into the recording tableau, it never moves. This is a great news. This means that if you have an infinite sequence of numbers, it makes sense to speak about the corresponding recording tableau. Okay, so let T be the outcome of RSK, outcome of the recording tableau, applied to this sequence of W's. Since sequence of W's is random, you get a random infinite standard Young tableau. You can think about this construction of Wierzch and Kerov as a kind of homomorphism between two probability spaces. On the left-hand side, you have this super nice, super easy probability space related to independent random variables. On the right-hand side, you have a complicated probability space, a random infinite standard tableau, which is its distribution is called Plancherel measure, and it appears in lots of places in representation theory. Okay, so it's a homomorphism. That's nice. This allowed Wierzch and Kerov to solve some problems. However, it would be even nicer if this homomorphism would be an isomorphism. So the question is, can you actually invert this RSK map? Can you find an inverse? The first time I thought about this problem, I thought it's a really stupid idea, because the classical RSK is a bijection, and in order to invert it, you need information which is contained in the recording tableau and in the insertion tableau. Here, half of the information was removed. We have no information about the insertion tableau. Can we find an inverse? And the answer is positive. In fact, it's related to our visual games related to exhibit B. All right, so let's have a look how to construct this inverse. The way to do this is to apply something called jeu de taquin. We start with an infinite standard Young tableau. This tableau was obtained by applying the recording tableau to some infinite sequence of W's. Jeu de taquin consists of 3 easy steps. And the first step should remove the corner box. This box always contains the smallest number, 1. In this way, a hole is created. Now we will slide this hole. Always, we should slide it either to the left or to the top, or to the right or to the top. And we always have a choice. We always can slide either the box which is to the right or to the top. And the answer is you should always choose the number which is smaller. Here we have a choice between 2 and 4. So we slide 2. Now we have choice between 3 and 5. We choose smaller number, 3. We continue in this way. After performing an infinite number of slides, you obtained something which almost looks like a standard Young tableau. The only problem is that the numbering of boxes starts with 2. If you are concerned with this tiny problem, you can simply subtract 1 from each entry, and in this way you obtain a usual standard Young tableau, an infinite object. All right, so what is the outcome of this sliding procedure? The outcome is twofold. There are 2 pieces of information. Firstly, we got a new tableau, and it's a classical result from algebraic combinatorics that this new tableau is also an outcome of RSK, also outcome of applying the recording tableau. However, not to original sequence of W's, but to a sequence of W's with the first entry removed. That's an interesting property. The second piece which you get out of the slidings is this blue zigzag trajectory. All right, what kind of information can we get from this picture? As you noticed, I like very much visual objects. So what you get is a very big zigzag line. And I spent lots of time looking on structures of these zigzag lines, looking for some structure. All right, so the question is, can we find some information behind this zigzag line? And the way to do this is to fix some large integer n and to look on the boxes. These are drawn with red color, boxes which in our tableau are small, which are at most n. On this picture, there's also a green box. It's located here. This green box is the last box along my blue zigzag line, which is still red, which is the last box along my Jeu-de-Daquin path, which contains a number at most n. What can we say about the position of this green box? It turns out that this relationship between Jeu-de-Daquin and removal of the first entry from the sequence has a consequence. The green box can be alternatively described as the difference of two Young diagrams. In one, we apply RSK to a prefix of sequence of prefix of length n, and we subtract RSK applied to the same prefix, however, with the first entry removed. RSK is an algorithm which has a lot of amazing symmetries. For example, if you read your word backwards and you flip the entries by reversing the order of the interval 0, 1, it turns out that this doesn't change the shape of your Young diagrams. This means that we can rewrite the position of our green box as a difference of two different Young diagrams. Again, we apply RSK, to certain sequence. But as you can see, this sequence is related to sequence of W's in the backward order, and also each entry is flipped. I replace each entry by 1 minus this entry. Oh, this is very nice. As you can see here, I'm comparing two Young diagrams related to RSK, which differ by the last box. This means that the green box is the same as the end of the bumping route when you insert a new entry into this specific tableau. All right, so this means that it's the same objects which I studied with Dan Romik earlier during this talk. And in the polar coordinate system, I have very precise information about where to expect the position of this box. This means that there is certain asymptote, there is certain ray which emanates from the center of the coordinate system. The angle of this asymptote is given by this angle in the polar coordinate system. So this means that if someone gives you only the blue zigzag line, you can find the asymptote. And this way, you can recover the first entry of your sequence W1, W2, and so on. All right, so this means that just by looking on the asymptote, you can get information about your original sequence of W's. What I showed you is that how to recover the first entry from your sequence. It's not a lot, but if you'd iterate certain argument, there is a way to recover also the remaining entries of the sequence. So there's a positive answer. Yes, the inverse to this infinite version of RSK exists. And in this way, there is a very nice isomorphism between these two probability spaces, which allowed us to solve some old problems related to dynamical systems related to this infinite tableaus. If you like this kinds of zigzag lines and animations, I have good news for you. There is a recent preprint of myself and Łukasz Maślanka, who is in the audience, where we apply this kind of jeu de taquin in more contexts, and we are studying dynamical systems related to the one we are seeing here, dynamics on finite tableaus as the boxes are inserted in the corners and they flow down to the origin. In fact, as usual, you should apply our new visual viewpoint and ask questions for some phenomena which you might encounter by looking on this kind of animations. This talk comes to an end. I think the moral which I would like to leave is that these asymptotic and visual problems which we encounter by running computer experiments can create new questions, some of which are interesting also for the algebraic combinatorialists. So I would like to encourage you to leave your zone of comfort and to look for this kind of asymptotic phenomena in your research. I would love to hear the feedback from you, how to find asymptotic versions of your favorite problems. If you have more questions, which I cannot answer today, I have good news for you. Two of my co-authors are present during Fpsac, so I encourage you to ask more questions during some coffee breaks. Thank you very much for your attention.
Thank you for that wonderful guided tour. Questions from the audience, even from the co-authors.
When you first said that you would like to find the inverse of the RSK, you said that it's a bad question because you're forgetting the insertion tableau. But I don't understand how that problem goes away.
In fact, the trick is that I'm cheating a little bit. Namely, when I'm constructing an inverse, this is a map which has the property that if you follow the arrows, so first you go along this line and then backwards, typically in mathematics, you want to get an identity. However, here it's a probabilistic problem. So you get identity almost surely. So you get identity on a set of almost full measure, on a measure of so you don't get the right answer with probability 0. So this is a typical trick which probabilists do. They identify two objects if they coincide except for probability 0. So this inverse is a bit tricky. Yes, in general, you cannot find an inverse, but if your object is random and you want to answer only almost sure answer, then by such a cheating, the inverse exists.
Thank you. Just one more question. Does it matter at all what the probability distribution on the omega is? Does it have to be uniform 0, 1 or?
Oh, that's a really cool question. So as long as this probability has no atoms, then you get the same probability distribution on the right-hand side. If you get your probability distribution has some atoms, then you'd get some other probability distributions on the right-hand side, which correspond to other also interesting representations of S infinity. And Vesh can care of explain how to produce even complete set of these representations by slightly modifying RSK. This is a long and fascinating topic. If you want a more precise answer, please send me an email and I will try to give you reference.
Okay, let's thank Piotr once again.
Thank you.
Okay, now we move seamlessly on, as we did in the morning. Next talk. Oh no, I think they'll give you a. Is it good? Can you hear it? Can you hear me? Yeah. Switch on. Oh, switch on.
Yes, very good. Oh, I think I'm a bit loud. Can you tone me down a little bit? Okay. Can you hear me? Okay.
Yes. Our second speaker for this afternoon is Professor Martin Ruby from the University of Vienna. There is his title, Promotion of Trevor aspects.
So thank you very much. So this is joint work with Sam Hopkins, and obviously the picture on the right hand side is missing. So could you make the clicker work for me, please?
Oh.
Okay, I just used the computer, right? Is this okay? It works. So I'd like to start with a problem you may have seen before. So how many ways are there for 2n people to cast votes? So we have an election for 2 candidates, Alice and Bob, such that Alice and Bob both receive the same amount of votes. So both receive n votes and Alice never trails Bob. And the first few voting configurations are here. Very likely you have seen them before. You may know them as big words, but you may also know that they can be seen as linear extensions of this poset. And you might also know that there's a very nice formula enumerating these. And One thing I like about these words is that there is an action on them. So we like dynamics. The promotion of a Dick word, W, is defined as follows. You chop off the first letter. And then what remains is not a Dick word anymore, because now we have more B's than A's. We're going to fix this. So just imagine the first letter A is gone. And then we look for the first violation of our rule. So we have A, B, that's okay. A, B, A, that's also okay. A, B, A, B, that's okay. A, B, A, B, B, that's not okay because Bob has one vote too many. So what we do is we replace this B with an A and sort of move it to the end. And what you get is a Dick word, again, a voting configuration. So that's promotion on Dick words. Yeah. And one reason I like actions is that they have characters. So what's the character of a cyclic action? If the cyclic action has order n, that means you have to apply it n times to get the identity. Then for our purposes, the character is the polynomial of degree less than n, defined as follows. If I plug in an cave power of a primitive nth root of unity, the polynomial should evaluate to the number of fixed points of promotion to the power of k. So that's the one definition of character that will work for us today. And then there is a very nice observation by Dennis White in 2007. First thing is promotion on Dick words has order 2n. And second thing is we can compute its character. It's the most naive Q analog of the Catalan numbers. You just replace round brackets by square brackets, and it's not even very important what it is. Okay, now that's all. Oh yeah, and one very nice way to visualize this is as follows. There's a very natural bijection between Dick words and perfect matchings. And I draw the perfect matchings, non-crossing perfect matchings, excuse me, in a peculiar way on a circle. And this bijection has the following property. It intertwines promotion and rotation. So rotation of the matching is what you think it should be. And promotion is what I just explained. And now it doesn't matter whether you first apply the bijection and then rotation, or you first apply promotion and then the bijection. And from this, it's plausible that the order of promotion should be 2n because there are 2 endpoints. And, yeah. Okay, now that's not new, but now we are making things more complicated. We introduce a third candidate. So now we have 3n people to cast votes and 3 candidates, Alice, Bob, and Charlie. And of course, Alice should win, always. So Alice never trails Bob or Charlie. The relative position between Bob and Charlie is irrelevant here. So it may be that Bob is first or Charlie is first at some point, and then they switch and whatever. And here are the first voting configurations, and you see there are many. And again, there's a nice POSIT point of view. So these voting configurations are in bijection with the linear extensions of this POSIT. And somewhat surprisingly, Germain-Crévaras discovered a really, really beautiful formula for these. It's written here. This was in 65, so 1965, I should not say nowadays. So I wasn't even born then. Yeah, and it's beautiful. And one interesting thing about this formula is that there is not such a nice proof for it available. Well, it would be nice proof would be nice. Okay. Oops. And as you may have expected, there is promotion on these words also, and it works just the same way. You chop off the first letter, which must be an A, then you look for the first violation of our property, which is either a B or a C. You replace this B or C with an A and move it to the end. And then you get a Crevaras word again. And now the question is, what's the order of promotion on these words? And the very, very surprising answer is, it is nice. So the order is 6n. And moreover, if you apply promotion 3n times, so as many times as the word is long, then you just obtain the word where you switch all the B's and the C's. The A's stay in the same place, but all the B's become C's and all the C's become B's. And we also have a conjecture. So this is a theorem now. And we also have a conjecture about the character. And we have absolutely no clue how to prove this. Maybe brute force works, but we don't know and we didn't try. But it would be good. Okay, I invite you to do it. But what's really nice is we have a nice visual interpretation of this result. So we have a bijection between Crevaras words and something Kuperberg calls webs. And promotion intertwines with these graphs. And that's what I'm going to explain now. Before I do this, I just mention that promotion generalized to linear extensions of arbitrary process, and up to, I don't know, 2021 or so, there were 4 infinite families of posets known, where the order of promotion is very nice, namely these 4 infinite families, and now we have 5, which is good. So how do we compute the order of promotion? And here a rather naive idea actually works. If we take this voting configuration and you remove all the Charlies, just one candidate drops out, then you get the Dick word because Alice never trails Bob. And same thing happens if you remove all the Bobs. Okay, you get another Dick word. And I told you there is a nice bijection between these Dick words and non-crossing perfect matchings. Well, here you see it. And then the naive idea is to superimpose them, and we call it Crevaras bump diagram because that's a cool name. And now what we can do with this diagram is we associate a permutation with it. That's an idea which will come up again later. So I show you how it works. You see, maybe you see it's very light here. You see some crossings. There are some crossings here and here. And also there are some degenerate crossings here and here. So we call these crossings. And you start at some number, for example, at 3. And then you follow the arc. And whenever you encounter a crossing, you look up these 2 rules. And for example, you go from 3 to 2, you've just followed the arc, you encounter the crossing, and then you see, that's this rule, I should go back again. Okay, let's go back. So here is a crossing of 2 arcs. We are in this situation, and we come from here, so we should turn left, and so on. And when no rule applies, then we stop. And the permutation, and it's not completely obvious that it's a permutation, well, it's not hard either, is 3 is assigned the terminal city. There's a question? Above, yeah, here is the crossing, yes. So it's this rule. We go straight through. Okay. So the The blue arc would be here. The rules are not clear. So this blue arc would be here. So this is the left, there is a left to right direction in this picture. But actually, I'm not going to explain it in detail because I want to explain other things, and this is relatively minor, but I can explain it to you in the coffee break. So essentially, there are local rules which tell you which way to turn, and then you get the permutation. And then it turns out the permutation is almost enough to determine this W, the Crevaras word, but not quite. You need a sign. Essentially, the sign, you need a sign for each connected component of this picture. So here we only have one connected component, but there might be several. You need a sign for this, and we encode it as another word. So this whole word is one bit of information in truth. Namely, you can say whatever letter you choose here, it's B or C. And then these two words determine the permutation and the sign. These two determine the Crevaras. This is important. And now it turns out that using a very simple geometric argument, you can, which I will not explain in detail now, you see that the permutation for the promoted word is the permutation for the original word rotated. And rotation means conjugation with the long cycle, or draw the permutation in a cycle and turn it. And also the epsilon is obtained, the epsilon of the promoted word is obtained in a very easy way from the epsilon of the original word. And from this lemma, it's immediate that the order of promotion is 3n. Everything before is details. But now comes something extremely mysterious, and I really want to explain this. So this is Greg Kuperberg, and he invented webs. So webs as in for spiders. And for our purposes, an SL3 web is a planar graph W, just as you saw before, embedded in a disk with 3n wide boundary vertices, arranged counterclockwise, and such that W is trivalent, which means the internal vertices all have degree 3, and the vertices on the boundary all have degree 1. Or if you want to connect them, they also have degree 3, but then as you like it. Second condition is W is bipartite, so a black vertex has only white neighbors, and vice versa. And the third condition is W is irreducible. That's a strange condition. It means that there are no internal faces with fewer than 6 sides. So 6 sides is okay, 7 is okay, and so on, but 5 sides is not okay, and 4 sides is not okay. And it turns out that, well, that's the reason why they were invented. SL3 webs are in bijection with 3 times n rectangular standard Young tableau. And now something very mysterious happens. Oops. There is a bijection between Crevaras words and something we call Crevaras webs, which are SL3 webs without internal faces having a multiple of 4 sides. So we have this really weird extra condition. And also each connected component is assigned one of the 2 colors, blue or crimson. That corresponds to the epsilon we had before. Warning, irreducible has nothing to do with components. Okay, irreducible means something about the minimal size of an internal face. the question is, does it mean the faces have at least 6 sides? Yes. Yeah. So 6 sides is okay, 8 sides is not good, 10 sides is okay, 12 is not good, and so on. And this bijection intertwines promotion and rotation, which was in the picture at the very beginning. And how does it work? I show how it works to make you believe that it's mysterious. So it works in a completely naive way. You take this bump diagram we had before. That's the only reason why I introduced the bump diagram. And you break up crossings. So I said already, the bump diagram has a direction. So the arcs go from left to right. And so this is actually well defined. You can make this precise. Here I introduce this extra avocado edges. And so here I do it. For each crossing, I introduce an extra avocado edge. And then I write down the numbers from 1 to 9 on the circle. And I make everything straight. And then I forget the colors. One thing we actually can understand is that this picture will not have faces with 4, 8, 12, 16 sides. Why is this? We start with something like this. So this is a part of a Crevaras bump diagram. And since it is, since the color of the edges alternate, this must have 2K sides. That's obvious. And now we introduce these avocado edges. So we get 4K minus 2 sides. Okay. Interestingly, the converse is very non-trivial. So it's strange that this works. So it's obvious that you only get a web which does not have a multiple of it's obvious that you don't get webs where internal faces have 4 or 8 or 12 sides, but that this is actually also sufficient is completely mysterious to me. I did not yet explain why this works in total. Well, we pull out another math magician, and we invent, well, actually this is Alex Postnikov, invented some rules of the road. If you see a black light, go right. And if you see a white light, go left. Okay, so these are a bit easier. And if you start, where did you start? If you start from 3, I follow the road. I see a black light, I turn right. I see a white light, I turn left. Black, white, black, I end up at 8. And you get this permutation. And we can prove by following the rules that the trip permutation of the Crevaras bump diagram is actually the same as the trip permutation of this Crevaras web. And it was funny for us because we discovered it exactly in this sequence I told you. So we introduced, we found this Crevaras bump diagram and we're happy. Oh, we can show promotion as order 3 as 6n. And then we discovered these webs and we were even happier because it's the same as this very old trip permutation from 2006. And then we were even happier, meta happy, because Postnikov proved that the trip permutation determines, oops, there's a mistake, determines the Pleiadic graph. So it determines this graph. There's a mistake here, the uncolored graph. And now we do it for every component and assign the color and we get the Crevaras web. So as a corollary, we find that promotion of a Crevaras word is the same as the rotation of the Crevaras web. And with this mystery, which I still don't understand, I would like to stop.
Thank you for that more visual art. Any questions? Yes, or lots of.
So you have these mysterious conditions that you have right on the previous page here, right? So have you tried removing some of these and checked in the OS what they enumerate and see if you have?
We can actually enumerate them. So the question is, what happens if we remove some of these conditions? Well, for one thing, if the main condition is actually this with the 4 sides. If you remove this condition, you get SL3 reps, and these are just 3 times n standard Young tableau. Okay, and if you don't remove it, we can count them. Yeah.
And if you add
even so, we get a refined counting. We can refine with the number of components. Does this answer your question? Not quite.
Well, then you can add conditions, and I mean, you can not have a multiple of say 8 or not have a multiple of 3.
Okay, no, we don't get anything interesting. Well, we don't get anything we understand better then. Yes, thank you. So, yeah.
Young tableau rectangular heights with webs, etc. You didn't mention this.
Yes, that's the mystery. We don't understand it. Yeah, okay. How is this related? Excuse me. How is this related to the work of Peterson, Pilavsky, and Rhodes, where they have promotion for webs? So they use Kuperberg's webs to show essentially. So that's the. I think that's. I'm not sure whether this is the main theorem. They compute the character for 3 times n standard Young tableau. And I should also mention there's a big open question: what are webs for SL4 or SL5? There's no nice basis known for them. There are webs, but no basis set. So the question was, how is this related to the work of Peterson, Pilavsky, and Rhodes? And the answer is, we don't know. The webs just pop up for no good reason. And I would love to see some algebraic reason why they appear here, but we have no idea. And even we stumbled over them. So it was complete coincidence that we discovered this.
Could it be related? Well, I'm thinking of these words as being highest weight elements when you restrict to SL2 in 2 different ways. One, the natural way, and one with the epsilon1 minus epsilon3 roots. Can you see it from that perspective?
Not yet, but I'd like to talk with you about this. This would be brilliant.
I'm not sure if you have already addressed this during the talk, but if we replace 3 cross n with some other fixed shape, is there some version of the theorem that we get?
Excuse me, I did not understand the question.
So instead of considering 3 cross n standard tableau, if I fix some other shape and look at standard tableau of that shape, is there a version of webs that I get? Is there a version of Krevera's words that I get?
Not that I know of. And I think it actually, there was some work, but I forgot where. I might recall, but not in a very natural way. So 3 time rectangular standard Young tableau correspond to the invariant tensors. They are highest weight words. And if you don't have rectangular shape, you lose this highest weight property. So that's the reason why rectangular appears. It should exist for 4 times n or 5 times n, but nothing is known here.
Yeah, so I've got 2 questions this time. Right. So my first question is, you have these art diagrams for non-crossing set partitions. so you have these arcs for non-crossing set partitions, but then you also have set partitions where you have crossings, right? And then, so is there an analog for Creveras set partitions where you have arcs of two different colors? And if that is an interesting object to look at.
So the idea, so the question is, can we generalize to set partitions?
Yes.
Okay. It seems that it's not possible, or it's not completely obvious. So I mean, I could try, but it was, so one, especially Sam Hopkins, tried very hard to find posets with nice order of promotion. And as you see, up to 2021, only 4 families were known, and there was a lot of promotion advertisements to look for further families. And well, now we have one.
So if I can have one more question. Yeah, so you have a formula with a Q counting, right?
Yes.
I was just wondering if there's some statistic that comes up there. And can you plug in more variables?
Just a moment. I'm looking for the, you mean the Q analog?
Yes.
Here. This is a conjecture. We cannot prove this.
But for the version that's known, the original version.
This?
Yes.
Oops, it's a major index. Or a major index, some major index. Yeah. No, I don't think we don't have a statistic yet. But to be honest, I did not look very hard into this. I checked the formula for numerically to reasonable size. So I'm absolutely sure that it's correct. But no, not absolutely. I'm quite sure that it's correct. Yeah. You see the pictures get very large because of this condition, no multiple.
Okay, let's thank Martin once again. We break for coffee and reassemble at 4 o'clock for the next stop.
So please collect the TA forms and fill them as soon as you can. Indian participants and invited speakers. From the desk where you got the goodie bag.
1, 2, check 1, 2, 2, check 1, 2, 1, check 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 A check 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 not mute. Okay, just where is the clicker? Thank you. Yeah. Okay.
Okay, we are ready for our next talk. Our next speaker is Professor Yuval Reichman from Bar-Ilan University, and he's going to tell us about cyclic descent extensions and higher Lie characters. Professor Reichman.
Okay, thank you. And thanks the organizers for doing this great work and during these difficult times, and for renewing the in-person conferences, which is great for us and something, a very successful conference, and to see all young people coming into the field, it's for me, it's making me very happy. Okay, so we will speak about the cyclic descent extensions and higher Lie characters. So the talk will consist of two parts. First part, I will try to explain the concept of cyclic descent extension. I apologize for those who heard this part for me many times, but many people are not familiar with this. And the last part will be to explain in brief what are higher Lie characters and how do they play the role in solving problems from this field. And the middle will be the main result. Okay, so it will be short, just to one slide to present the main result. Okay, let's start. So we start with the descent set of a permutation with just the set of positions where the value decrease. And this is very classical. Some people trace it back to Euler, even so I'm not sure that Euler, the generating function was studied for sure by Euler. And the cyclic descent was defined by, let's say cyclic descents are descents, but we also compare the last position, the value of the last position to the first one. So n could be a descent. These are cyclic descents. They were introduced by Kliatchko in '74 in a paper about Lie algebras, which was ignored by the community of algebraic combinatorics. But then in the 90s, there were two papers of Cellini that picked attention, and there are many follow-ups of these papers of Cellini that introduced cyclic descents in the context of cyclic descent algebras. Anyway, okay. So, and there are descents and cyclic descent, there are descents of standard Young tableau. So they were, I suppose they were introduced by Schutzenberger, or maybe he was the first to realize that RSK defines naturally descent set on a standard Young tableau. If it's not Schutzenberger, please correct me, but anyway, so what are descents? Descents are where I is in I plus 1 is in lower row than I. For example, here, 1, 2, 2, 3, 3 is down, 3, 4, 4, 5. So the value here, 2 is the descent, 4 is the descent. So the descents here are 2 and 4. So while in permutations we look on positions, on Tableau we look on values, and there are good reasons for this, not to be mentioned now. Anyway, while it was very natural to define cyclic descents on permutations, comparing last positions with first position, it could be bigger or smaller. Here, n could not be in a higher low than 1. in any standard Young tableau, one is in British way of writing, one is in the first row, so n could not be cyclic descents. So this was the first problem that was discussed with Vic Reiner, Onadin, and other people, but it was discussed before by Brandon Rhodes and others, we will see. Define a cyclic descent for standard Young tableau of any shape lambda. Okay, so cyclic descent set for any standard Young tableau, I plus n could not be in a higher row than 1, so we should see what are the properties, what are the important properties of descents, that the cyclic descents that we would like to see in Young tableau. Okay, let's look at this sequence. This is series of shifts, of rotations. So 3, we shift the permutation, 3 would be in the first position. Now 4 is in the last position, now first position, so etc., etc. And so this is, there are 5 permutations in this orbit of cyclic shifts or rotations of permutation. And the descent set is not so clear what's going on with descent set, but with cyclic descents, okay, we see the red letters are where the cyclic descents are located, and you see 2, 3, 5, 3, 4, 1, 4, 5, 2, etc. You see that a shift, rotational shift of the permutation shifts the cyclic descent. So this one property that we would like to see. And also another property that if you take off, if we delete the letter n, we recover the descent set. So the cyclic descent set of this, of rotation action on symmetric group satisfy first, if we delete n from the cyclic descent set, we recover the descent set. And second, there is a rotational shift that increase the values of this descents by 1. Okay, so there was a work about this by Brandon Rhodes, pioneering work like 12 years ago, about rectangular, standard Young tableau of rectangular shapes, and Rhodes proved that there exists a cyclic descent map on standard Young tableau of any rectangular shape, such that if we delete n, we recover the descent set, and the Schutze-Berger, Joux-de promotion that was mentioned in previous 2 talks shifts the cyclic descent set by 1. Okay, good news. So motivated by these results about Cellini, about symmetric group, and Rhodes about standard Young tableau, we defined an abstract concept. Oh, let's see an example of Rhodes. So this is, you see the promotion, we have seen it. So you start with this tableau, you end with this tableau. And here you see the descents are 1 and 4. Here the descents are 2 and 5. So this was what we would like it to be. And you see here are the tableau. These are the orbits. This tableau is mapped to this one to this and back. And here we should ad hoc add 6 as a cyclic descent. Why would not explain now. And here we should also add 6. You see 1, 3, 2, 4, 6. And so these are 2 orbits, and the, let's say, generalize the abstract concepts. Okay, given a set of combinatorial objects T and a map, descent set map that map any element to a subset of n-1, the cyclic descent extension contains a map. Any element has associated subset of 1 to n, not of 1 to n-1, but 1 to n, and a bijection, which should be a rotation or promotion on the set, which shifts the cyclic descent set. And if we restrict it to first and -1 letters, we recover the descent set. Surprisingly, there is here a third axiom or property, which is not so transparent at first glance. And this is non-Escher property. The cyclic descent set of T of an element could not be the full set or the empty set. And why? Why we call it non-Escher? This is because of the Escher famous drawing. I don't know how well you see it, that illustrate the fact that you can never walk up forever or walk down forever. This is a moral for life. If you are down, know that there is a point you will go up. And also if you go up, remember that you will sometimes go down. You cannot go up. And this illustrates the paradox of permutation cannot have Cellini cyclic descent set, empty set, or full set. And also in words, if you take all rectangular shapes except of one row or one column, then this is a good illustration. So these are two examples for this. And why do we need the third axiom? The third axiom gives rigidity for the theory. For example, the cyclic descent set distribution is unique, is defined uniquely. It's not, the cyclic descent extension is not unique, but the distribution of cyclic descent set is unique. And this is thanks to this. Also, all connection to representation theory that some of them we'll see later, some not, are thanks to this axiom. Without this axiom, we are in a zoo. Okay. So, okay, what is the answer for standard Young tableau? The answer for standard Young tableau is that these are called hooks, hook shapes, one part bigger than one, and the set of standard tableau of any given shape as a cyclic descent extension if and only if lambda is non-hook. And the proof that we had with Vic Reiner is algebraic. It involves Postnikov toric Schur function and Gromov-Witten invariance. We can say more, it involves some positivity properties of Postnikov toric Schur functions under certain substitution specializations, simple specialization. But this is important because if the positivity say that there is a combinatorial realization. If there is no positivity, no combinatorial. There is something abstract maybe, but not combinatorial as we want it to be. And now there is a second proof given by Bryce Wang, purely combinatorial proof, and this proof is I should make some add to this because I think he was a very talented student in MIT and shifted to theoretical computer science, so people do not know of this. So this involves twisted Schutze-Berzé promotion for any shape and skew shape. And what was Tom Robbie told us that very few shapes are behave like coherent with Schutze-Berzé promotion. For the Bryce Wang, all of them are coherent up to, let's say, you will see, his paper is long, and this is some conjugated or twisted Schutze-Berzé promotion that at least it gives a combinatorial proof to this statement, and he shows that Rhodes, for example, is a special case of his promotion. Like for rectangulars, the Wang promotions is the Schutze-Berzé. Just okay. Question?
This theorem, is it about a cyclic descent extension for the promotion that we saw specifically, or for any?
No, there is a bijection. We do not know the bijection. This is existence theorem.
So if it's
existence, okay. Bryce Wang illustrated one let's say, twisted conjugated promotion that will prove this theorem combinatorially. Our proof is not constructive at all, just say its existence. Okay.
One more question. So that need not be unique, right?
It's not unique for certain shapes. There is a paper when this is unique for shapes which are close to hooks. For hooks, there is no. For shapes which are very close to hooks, nearly hooks, it's unique. Okay. Significance of CD, let's go quickly.
Sorry, there's one more question.
Yeah. So just I started at 4:05. That's yeah.
Just to understand the cyclic descent extension definition, is there some example of a set and a descent function where the non-Escher property is not true, but the other properties are true?
The which property? Non-Escher, there are in the paper they are discussed. There are, but this is like esoteric examples. Okay. Significance of CD quickly. So it's enumeration thanks to due to non-Escher property. There are very nice enumerative like cyclic Eulerians, etc. And twisted promotion by Wang. Cyclic descent algebra, cyclic quasi-symmetric functions algebra with Ira Gessel and Vic Reiner and Ronadin, and Postnikov-Turek sharp. In this talk, we will see connections to Eierly algebras, characters, and they are geometric. It's related to Steinberg-Torus due to the works of Peterson and Stambridge and to Gromov-Witten invariants due to works of Postnikov. So it's related to many branches in mathematics. Okay. So what is the problem that we will focus? Which conjugacy classes carry cyclic descent extension? Not, but Cellini is not working. Let's see an example. Cellini is not working. Let's take 4 cycles in S4. There are 6 4 cycles. What are the descents sets? 3, 1, 1, 2, 1, 2, 3, 2, 4, 1, 3. Is there any extension? Could we ad hoc? If we, let's say, not ad hoc, if we will see the cyclic, okay, this is Cellini, you see 4 here. So the only permutation, the only 4 cycle for which last letter is bigger than the first one is this one. So 4 appears only here. And this is not a cyclic descent extension. Why? Because if we see here 1, we should see 2. You know, it should be closed under cyclic rotation, the sets, and they're not. So this is not a CD. On the other hand, ad hoc, if we will add to all singletons the letter 4, then we will get a cyclic descent extension. But this is some misleading example. So in this case, we just add to the singletons. If we make all cyclic descents of same cardinality, many times it works, but mostly we could not do it because for most conjugacy classes, the range of cyclic of descent set cardinality or descent number is big. Okay, so this trick is not working. So anyway, the question is not easy. And to show the first sophisticated example, I thought it will take me 2 slides, so I will not show. Let at least S6 or whatever. Anyway, what is the main result? The main result is that a conjugacy class of cycle type mu has a cyclic descent extension if and only if mu is not of the form R to the S for some square free R. So, for example, if there are distinct cycles of distinct lengths, this is always okay. If not, n cycles, they should be square free. And R to the S, what's important is the R, that R should be square free. This is the result, and the proof is algebraic and involve hierarchy characters. And unfortunately, we do not have, even so I try to publicize this problem, find a constructive combinatorial proof. So now there is a progress, but not for this conference. So for involutions, we can do something on the spirit that was described by Tom Robbie, but not. So if we should combine Sheila Sundaram bijection from involutions to oscillating tableau and Stanley Chen and whatever, and Dennis White ideas, and then we have something. The bijection is complicated, but we have we make it after complicated bijection. This is just rotation of certain web-like or even certain matching on the rotation clockwise or so, but this is after anyway. So this is just for involution. We do not know how to generalize our proof to other conjugacy classes. Maybe we can do block partition, like set partitions, but not anyway, partitions to blocks, but no conjugacy classes is very far from our horizons. So no combinatorial proof. Okay, so now I should go quickly. What is the main ingredient? Main ingredient our proof. Our proof is proof of existence, not constructive. So we look on quasi-symmetric function. So the quasi-symmetric function, there is like what people call the quasi-symmetric generating function for the descent set of a conjugacy class. This is it's not a symmetric function. If you're not used to, so there is a language of characters. So there is the pre-image of this. This is n variables and the descent set. We count. This is a generating function for the descent set over the conjugate. No, n is just to int. You can raise the n. That we take the n in each summand there are n variables. Just this. Just to enumerate. People do not write it for some reason, but it should be written because it's confusing. You have f sub b. What is b in what in subsets of mushroom, subset of something? Okay. Now, okay. So there is a longer before it was this definition. Hierarchy character is the pre-image of this. This is a symmetric function. This is well known. And the pre-image is an induced character. So this is a sure positive symmetric function. And this is induced from one-dimensional, one of the one-dimensional, like primitive, like you can think, linear characters of an element, of the centralizer of an element to the symmetry group. And this is the representation, and this is called hierarchy character. This character is the hierarchy character, and I would not go on classical result because it's important, but the hierarchy character, there is a 80 years old problem, very famous problem that many people worked about this, Kraskevich Wayman, Gessel Rotoner, Sheila Sundaram, Shoker, Vic Reiner and Hersch and Swanson, other people, about this, to decompose this representation, the hierarchy character into irreducibles. We know that this is true positive, so this is a proper character. It's not virtual. What are the multiplicities? We do not know. And to solve our problem, we should have some information on the multiplicities. And this is next slide. Okay, so we consider this is for any set, but you can think the set to be conjugacy class. The conjugacy class A has a cyclic descent extension if and only if two conditions hold. we look on the multiplicity, the hook multiplicity is generating function in the higher Lie character, and it should be divisible by 1 plus x, and the quotient should have non-negative coefficients. And the easy part is the first part. The visibility is much easier. And this part is difficult for some conjugacy classes, you will see. Now I will go, okay. So the visibility, there are two. First of all, the hook multiplicity is generating function is divisible by 1 plus x if and only if the evaluation of the full cycle on this representation, the character of the full cycle on this representation is 0. And we know that the higher Lie character on full cycles is if lambda is equal to r to the s is Mobius function of r, otherwise it's 0. It's related to some classical results of classicals in algebraic combinatorics, some well-known results of Adrian Garcia and Michel Vax. So there is a combinatorial proof for this, and we give an algebraic proof for this formula. We give two different, one anyway. So this could be less than 1 page proof, so it's not so difficult. And this dilemma of divisibility on non-negativity also not so difficult. The difficulty is to prove non-negativity. Okay, if there are distinct cycles, there is a factorization lemma. If the partition is nu and r to the s, this here nu is free of parts of length r, then there is a factorization lemma which proves the divisibility and non-negativity after dividing by 1 plus x. These are generating function of hook multiplicities. So this is non-negative and this is easy part, the easiest part. Next, n cycles. Here we apply a formula of Shila-Sundaram for the sum, the multiplicity of the sum of multiplicities of two consequent hooks. And applying this, we can prove, it's not so easy, but we can prove that the multiplicities of the hooks are unimodal and sometimes also long concave. We will not speak about this, depending on the visibility properties, but because they are unimodal, non-negativity follows. Anyway, the difficult part is R to the S, and I have not much time for this, but here, first we consider generalization of the hook multiplicity generating function. This is for, we fix R and round over S, and we take the sum of two. This is E sub k time elementary function, elementary symmetric function time homogeneous is the sum of two consequent hooks. Anyway, so this is it's easier to analyze this more complicated object. And if this more complicated object, if this has non-negative coefficients also, this has non-negative coefficient, and it's easier to prove that this has. How? By generalizing Sundaram. We generalize Sundaram lemma, and for not just Sundaram, he gave a very beautiful formula for the multiplicity of two consequent hooks in the Lie, no higher Lie character, which is n cycle. Like in code, now if we wanted to do it for R to the S, this is becoming much more complicated. The advantages of this formula that for the what we saw to be very difficult ER to the S, we have just multiplicative formula. And multiplicative formula, if you can analyze each of the factors and find that they are non-negative, then altogether it's non-negative and it's easier. So this is like 10 10, 15 pages proof. So this is the core, and I really jumped over it. But let's come with some moral. I have 2 remaining minutes. So not moral, challenges. So first, all the moral is, some people would not like, is that you can do more with algebraic proofs than you can do with combinatorial bijections. Even so, they are more difficult and you should study a lot and you use lots of tools. At the end, if you have structure, the structure promises positive answers. Why it should be positive? Because there is some representation behind. But there should be combinatorial, like more elementary, or that easier to explain with beautiful and visual, like visual art. We said, like to come to museum. There is, if I would like to see something that you just rotate the elements in the conjugacy class and they look something like webs or something like I don't know what, and you rotate them and you get it, and you get the cyclic descent extension. But we do not have, and the difficulty is R2DS. Also, not half combinatorial is a proof that this, for any partition lambda, the Hooke multiplicity is generating function of the in the hierarchy character is unimodal. One can translate it to purely combinatorial statement. This says that if you measure, you count how many elements in the conjugacy class of cycle type lambda has cyclic descent prefix of length k. There are papers of Thibon about this, and so, but they did not give the information that we want. If you can prove that for any conjugacy class lambda, the number of elements having descent set prefix of length k is unimodal, this is a shortcut for a proof, then it will show that 15 pages of algebraic computations are needless, maybe important for the algebra, but not really needed here. But we cannot do it just for n cycles. We can the shortcut works. Okay, so thank you for hearing me. Sorry for being late of time.
Maybe just one quick question, if anybody has. If not, let's thank. Oh, sorry.
Quick question was just if you had a generalization for the multiplicity of, instead of a Hooke, a product of two.
Generalization of the multiplicity.
A multiplicity with a partition with 2 rows.
So we didn't try 2 rows. I think for hooks, like one cycle, k cycle, one can do it. But you do it for n cycle, and you also distinct, so you combine. So this will give. So for hooks we can do it. For 2 rows we did not try. So, and I believe it could be that for 2 rows it will be easier to prove unimodality. But we did not try. Okay, thank you.
Thank you.
He said that he forgot one time the mic with him, and he went to his seat and he said the audience didn't understand anything. So I must say that the audience was responding, and I was happy with questions.
Thank you. So as our next speaker gets ready, I'll introduce him. It's Professor Isaac Conan from the University of Claude Bernard Lyon. He'll talk to us about multi-grounded partitions and character formulas.
Okay. Does it work? Hello? Can you hear me? Okay, it's fine. No. Click, yeah. Click on the sounds. No, on the computer. Okay, then, okay, that's fine. Well, thank you to the organizers. So we'll talk today about a work that I did with Jean Dus, and it is about multi-ground partition and character formulas. So the full article, you can find it in the full article with the same title in Advanced in Mathematics and with this exact reference. So I'll try to be very light for this last talk. So if you have to understand something, is it just this light that I put on the first position? So what do we compute exactly? So we compute character of standard modules. So standard modules, there are some kind of representation in the for affine Lie algebra. So it's not the group algebra, the group Lie group algebra, but it's affine Lie group algebra. Affine Lie algebra. Sorry. So what are the existing methods to compute these characters? So the main formula that we know is the Velka character formula. And the thing about this formula is that when you have the character, at first it is sum of exponential of what we call the weights. And so you have a sum with positive coefficient. And in this formula of Velka, we do not have an obvious fact that the coefficients are all non-negative. But there's a way to retrieve this fact. It's by doing what we call the principal specialization. So the principal specialization is a kind of transformation. But when we do this transformation, there is a lot of data, a lot of variable that we transform into one single variable. So there's a lot of information that we lost by doing this, but we obtain a product, which is really nice. And there are also some other methods. So what we call the vectors operator method. It permits to have what we call forbidden pattern. So you express so you have a kind of base in the character that you want to express in different ways, and via the vectors operator you can express this as some basis for where we do not have some forbidden patterns. And why is this interesting? It's because by doing these two methods, we have what we call we can have what we call Roger Ramanujan type identities. So yes. So for the product side of the Roger Ramanujan type identity, you can have it by using the principal specialization, and the sum side is obtained by doing the Vetus operator. So what we have as another method, so what we are interested in is the method called the perfect crystals, and a formula related to it, which is the KMN square character formulas. So this is obtained by doing some sum over what we call the lambda path. So we'll briefly introduce this later. And what we bring to the table, what we add, is that we make a bijection between this lambda path and what we introduce as a multi-ground partition. And by doing this, we simply express the character as a generating function of multi-ground partition. So this is what you have to you have to retain for this talk. So I will now introduce what is a multi-ground partition. But first, what is a partition? So a partition in the sense of integer partition. A partition is a non-increasing finite sequence of positive integers. So we have example 4, 3, 1, 1, and the sequence 1, 1, 1, 5 times. So what we study in our paper is something slightly different. So for that, we have to introduce a set of what we call a set of color. And we suppose that the integers occur in these colors in the set C. And we also add a binary relation on the set of colored integers. So an example here is that we take a set with 2 elements, and this relation is in order on the set of color integers in such a way that we have that 1 C2 is always greater than 1 C2, and is greater than 1 C1, greater than 1 C1, and so on, and will decrease in size of the integer. So by introducing this definition, the color, the notion of color integers and the binary relation, what we have is that we slightly modify this definition by doing this. So what we call a generalized color partition, so according to the relation, the binary relation that we introduced there, is a well-ordered finite sequence of colored integers according to the relation. So you have to take a finite sequence, and which is well-ranged according to the relation that we have here. So for example, with this order, which is a relation, we can have that the sequence 3C1, 3C1, 2C2, 2C1 is a generalized partition according to our order, but not 2C1 to C2 because they are not well ordered. So now, what is a multi-ground partition? So for that, we have to make an additional assumption. So you have a set of color, the integers colored, and the relation. And you suppose that you have T colors such that when you take these T integers color, which are unique, you have the sum of the integers, which is 0. And it's a kind of circle. They are well ordered, but it's a kind of circle that you obtain by doing this comparison. Okay, so the multi-ground partition, what is this? with ground CG0, CG T minus 1, and with the relation that we defined above. It's a non-empty generalized color partition such that the T last integers are what we have in our assumption. And we have the condition that the T integers before there's T last integer they form a different sequence. So because we do not want to repeat this sequence at the end of the partition. Okay, so an example for the multi-ground partition. So you consider these matrices, and you suppose that when you have three colors, and you suppose that two elements are well ordered if the difference between the integers is greater than the coefficient in these matrices. So these matrices is, so the B is for the row, and the B prime is for the column. And by doing this, when you choose G, so the two color to be C1 and C3, but you must have that the integers must be -1 and 1 and -1, and you have the following allowed multi-ground partition, and this one is not. These two one are not allowed because here there's a repetition. And here we do not have that the difference between those two is less than what we have in the matrices, which is 2. So now if you want to take a nap, this is the time for the 3 next slides, because we'll briefly talk about what is a perfect crystal and what is the KMN character formula. So it's not a definition, is just an enumeration of what these notions are. So we have the perfect crystal that we take G to be an affine Kac-Moody algebra, and you have what we call the simple positive root, and also the null root, which is a sum of the simple positive roots. And then we also have what we call a dominant weights with a level L, and you have the notion of crystal of level L, which was introduced by Kashiwara and his co-authors, and the notion of energy function on what we call the tensor product. So all these notions I won't detail them. I'll just mention them because they're what matters here is the combinatorial interpretation in terms of multi-grounds. And for such crystal, and such dominant weight, you have what we call the ground state path, which is a particular sequence. Here is written as a infinite product of tensor. But here, what you have to understand is that this sequence is periodic. And in particular, what we call the lambda path. So it's a sequence when you take the element in your crystal, and it has to be equal to, starting from a point, it's has to be equal to the ground state path. Okay. So the KMN character formula. So what is the KMN square for? So it's 6 authors, and two of them have the first name beginning by K and M and N. But it's better than that. It's the 2 first letters of each name. So that's quite interesting. Maybe we can rename it. And the KMN crystal-based character formula state that when you have when you want to compute the character of the the standard model. So this is what we which is what it's called irreducible high test weight UQG at module. So this is what we call the weights. So this is this sum which depends on what is a weight of an element of the crystal, and which also depend on the energy function. And the character is defined by this sum over the lambda path. So this notation is for the lambda path. I had to change it. Sorry for that I keep the notation there. So starting from this formula, we say that so the formula for the weights was really close to some size of partitions. So in what we call color partition, there is a way to have something similar, but it's not very similar because of this difference, which happen to be different at each step, at each G. So we had to, what we said, we normalize the energy function. So we take a perfect crystal, the level L dominant weight with ground state path, and this time the period is T, it's T, sorry. And G an energy function. And then we normalize the energy function. So we take the function and we subtract this means over the period. And again, we add another assumption that we take a D, which is a suitable divisor of 2, such as these two values are always integers. So with this assumption, we have that by considering so the set of color to be the set indexes by the crystal, and the relation defining by this difference according to our normalized energy function, we have that the multisets ground partition according to this relation is the set of non-generalized color partition, which end by these T color integers in such a way that we have this relation that we have in the definition of multi-ground partition. So the T integers, color integers before the T last one must define a different sequence, and you have the exact value of what UK must be for K from 0 to T minus 1. And with this definition, you had another assumption to the set to be that we consider is the multi-ground partition with our ground, say G0 and say so on and say G T minus 1, and the relation that we defined in the previous slide. And the two additional conditions are that first one, the number of the part are the element that compose our partition. So the number of parts must be a multiple of T, and the difference between two consecutive parts, it's not a multiplicative. The difference between the two consecutive parts minus this element. So there is a mistake here. It's not this difference, but this difference minus this expression must be a multiple of D. And with these two additional conditions, you have that to compute the character of our standard module is just to compute is equivalent to compute computing the generative function of this set of multi-ground partition, and you have a factor 1 over QD, which is what we call the Pure-Sharma symbol. So it's an infinite product, so which is not relevant to define here, but it's express some partition. And this CP, how many do you have? 5. Okay, I think it's quite plenty. So the CP is for the product of the color that appear in the partition, and this symbol represents what we call the size of the partitions, which is the sum of the integers that compose the partition. So this theorem is really a generic method, because it's whenever you have a type, whenever you have the crystal of a certain level, you can just build a suitable set of multi-ground partition to have the character. So we take the example with the level 1 standard module of the Lie algebra A2 minus 1 power of 2 for n greater than 2. And you have this nice formula with there's a change of variable. So this is a product of Q series of a Q Poisson symbol. And here the E, this operator is just the mean of the function, and the function where we change all the parameters C, the color C, by the opposites. And you have this nice formula. So how do you find this formula? Simply, you take the crystal. So this is something which is in the literature. So you have many study of what is the perfect crystal for the classical type. So all we have to do, we do not have to do the algebraic study. We just have to take what is existing, and then we just interpret it in terms of multi-ground partition. And you have so this perfect crystal for the type A2 minus 1, 2 for the level 1, and there is only two level 1 weights for this type, which are lambda 0 and lambda 1, and these are the two corresponding lambda path. And the energy function is given by these matrices. So in these matrices, you have to understand that what I say H B1 product B2, you read the B1 according to the column and the B2 according to the row. And for example, here the one overline is this one. And with this, for the character of the lambda, the character for the lambda 0 standard module, you have so this interlacing sequence of overline 1 and 1 as the ground state path. And for this value of d, small d, capital D, small d, and t, you obtain that u0 and equal -1 and u1 is equal to 1. And you have the integers that you obtain are the odd color integers with our set of color, and with this particular partial order. In particular, why you have these two are not ordered, because there is an interlacing sequence. They can form an interlacing sequence of integers. So you have 2k plus 1 C1, which is less than 2k minus 1 C overline 1, and so on and so on and so on. And by doing this, when you try to compute the multi-ground partition, the generative function of this multi-ground partition, you obtain this infinite product. And by applying the formula, you retrieve the theorem that we have at the beginning of this session. And we do the same thing for lambda 1, which gives something slightly different. Here we have one overlay 1 and so on. And for the same value of d, capital D, small d, and t, we have these two elements. So before we had -1 and 1. Here we have the opposite is 1 and -1, and the generative function is slightly different for this one. So I will just end with a last slide. So what we have done so far is that we use our method to compute the character for the standard level 1 modules for this type. And we retrieve some classical formula given by Wakimoto for also these two type A to n power 2 for n greater than 2, and dn+1 2 for n greater than 3. And we also compute the character for the type A11, which is something which is really well studied because, for example, for the level 3, we retrieve the Roger-Ramanujan type, Ramanujan, not Roger-Ramanujan, but Roger-Ramanujan times a Q series. And what we obtain also is a identity with absolute value. So the relation that we had on color partition, on color integers, were defined by an absolute value according to the color we had. And what should be done is just to compute for the type CN1. So this is an ongoing work. So it is partially done, and to be crazy, you have to compute for, because the formula work for every level, all level of scalar type. So you want to apply this to compute all the standard modules. Thank you.
Any questions? Yes.
So if I'm taking a guess a little bit, you're using one particular realization, one very particular perfect crystal for each type. What happens when you change to some of the other perfect crystals?
No, the formula is for any perfect crystal for a certain level. So but we will have a different multi-ground partition. But at the end, the character is unique. So you have a different ways to express the same character as generative function of multi-ground partition.
So you basically understand the different types of how your combinatorics change when you change your representation. Yeah. Maybe I can ask a quick second question. What happened? Do you see rank level duality playing a role or giving you some identities?
For the type A n-1, we hide this. So you try to understand how the duality affects our generative function. It happens that in the generative function, what we have, there is a kind of streak such that you have two colors which become inverse each other. So this is why the duality intervened from this type. So for the other, we do not focus on this, but there is a kind of inverse that occur in our formula. Maybe that can explain the duality.
Are there any further questions? If not, let's thank
you,
Isaac, and all the speakers in this session. And I hand over to Arvind, our main organizer, for further announcements.
Okay, so we'll set up the poster marathon right now. So while they're doing that, a couple of announcements. So some of you have been asking about spouses, whether spouses or partners have to pay for either the excursion or the banquet. So for the excursion, no. For the banquet, it will depend on how many people we have in total. It is possible that we might be able to pay for them, but I don't know yet. I need to know the numbers. So please fill in the forms for both the excursion and the banquet as soon as possible. In particular, we will close down the numbers for the excursion by tomorrow lunchtime, because I need to book the buses. I need to know exactly how many there are. So please do fill that form. Yes, Gaurav? It's no, not online. No, as I said, please go to the registration desk. There is a sheet where you have to, against your name, you have to write how many people are accompanying for number 1 excursion, number 2 banquet, and number 3 the classical music program on Saturday. So for each, you please fill in some numbers. For the trek, I want to make some remarks. So for the excursion, I'm sorry. So this is at Shravan-Belgola, as I said. It's a hike. I mean, it's 700 steps roughly. You cannot use shoes. You'll have to walk either barefoot or using socks. This because it's a religious place. You have to kind of respect their rules. And they might also object if you come in Bermudas or something. I think they would expect some kind of quote unquote modest clothing. Yeah, so, and in case you are not able to, there are porters available at a cost who will take you up on a chair or something. So please keep that in mind before deciding. And one last announcement. Some of you have been asking about using the gyms on campus. If you want to do that, please give your names to Abhinandana, the secretary, again at the desk, at the registration desk. We will have to take specific permission for those who want to use the gym. That list will be sent to the gym, and from tomorrow onwards, you can use it. Okay. So if you are in doubt, put your name in. Okay. All right. So on with the poster marathon. Everything is ready?
Hello everyone, my name is Yan Zhuang and my poster is titled Refined Consecutive Pattern Enumeration via a Generalized Cluster Method. This work deals with the question of counting permutations by the number of occurrences of a given consecutive pattern. And one approach for answering this question is by using something called the Golden-Jackson cluster method. The main result of this poster is the lifting of this cluster method to the Malvigno-Reutnauer-Hopf algebra on permutations. What does this do for us? Well, first of all, if we apply certain homomorphisms to this generalized cluster method, we can get back both the classical cluster method as well as the Q analog, which keeps track of the number of inversions. But wait, there's more. We can use the theory of shuffling compatibility to construct other homomorphisms that allow us to refine by other permutation statistics. And this gives us an approach for counting permutations both by the number of occurrences of a consecutive pattern as well as by these permutation statistics. If this sounds interesting to you, be sure to check out my poster. I'm sorry I can't be there in person, but I hope to see you next year at Davis.
Mockingbird lattices by Samuel Gerardo. We all know ternary lattices, posets defined on a set of the binary trees of a given size, where the covering is this right relation. This is also known as the rotation operation of binary trees. This is the path diagram of the Tamari lattice of order 3. In this work, variation of the one of the Tamari lattices. The Mockingbird poset of order D is the poset of the trees reachable from the right comb tree with the internal nodes, and where all leaves labeled by M. We obtain these path diagrams for M of 2 and M of 3. The motivations of this work come from combinatory logic, a model of computation. As main results, we prove that all M of D are lattices, enumerate their elements, their covering pairs, and their intervals.
Increasing subsequences of multiset permutations. This is a joint work with my co-authors Alexander Clifton, Yifeng Huang, Sam Spiro, and Semin Yu. A multiset permutation in words is a word in letters 1 through n where each letter repeats a fixed number of times. In our work, we have considered random variables both random variables. We use techniques from formal power series and analysis for the first random variable, and probabilistic combinatorics and coding theory for the second random variable. Here is the archive number to our preprint. First random variable and formal power random variables. We use techniques from formal power series and analysis for the first random variable, and probabilistic combinatorics and coding theory for the second random variable. Here is the archive number to our preprint.
I'm Sheila Sundaram, and I'm here to tell you about row-strict dual immaculate functions, which we defined as a basis for the ring of quasi-symmetric functions, and we also construct a cyclic indecomposable zero Hecke algebra module for it. The action that we define defines a partial order on the standard immaculate tableau, and this poset is quite remarkable. It shows lots of other submodules and quotient modules. And finally, we complete the combinatorial and representation theoretic picture by showing that generating functions of all the possible variations of tableau can be obtained from this poset. So here's an example of the poset for the composition 223. The bottom and top elements generate cyclic indecomposable modules for our quasi-symmetric functions. Here are all the different variations on semi-standard tableau of a particular composition shape. And here's a slide with lots of details that you can also find in the paper. Thank you.
Good evening, everyone. My name is Anurag Singh, and this poster is about the homomorphism complexes, reconfiguration, and homotopy for directed graphs. This is a joint work with Anton Dochterman from Texas State University. In this work, we initiated the detailed study of homomorphism complexes of directed graphs, which are parameterized by graph homomorphisms. These complexes have applications in the study of graded posets and resolution of monomial ideas. We introduced the notion of directed neighborhood complexes and established a number of results regarding its topology. We have also studied the reconfiguration problem for directed graph colorings into tournaments. Various notions of directed homotopy for directed graphs have also been discussed. Some of these homotopy relate constructions from the literature. We hope to get your valuable feedback on this work. See you all very soon in the conference. Thank you.
Hi everyone, my name is Sergio Lizalde and the title of my poster is Walks and Simplices Cylindric Tableau and Asymmetric Exclusion Processes. Now, despite what you see in my background, I'm actually not in Bangalore, unfortunately, but you can still find my poster here on this website, dartgo.org/Fpsac. Just a very quick summary, we give bijections between three classes of combinatorial objects that have been studied in different contexts. The first one are standard cylindric tableau. The second one are walks in a certain simplicial region. And the third one are sequences of states in the totally asymmetric simple exclusion process. One advantage of our bijections is that they allow us to translate some operations from one setting to another. For example, if you use the cylindric analog of Robinson-Shenset insertion for Tableau, that translates into a bijection for walks that gives a new proof of a theorem of Courtiel and others. Check out the poster to learn more about it.
Hi, I'm Eran Nevo from the Hebrew University, and together with Maria Chudnovsky, we consider stable sets in flex spheres. Namely, look on all graphs on n vertices, whose clique complex is the d-dimensional sphere. In each such graph, look on the maximal size of a stable set, also known as independent set, and take the minimum overall of this size over all the graphs. This is the invariant we consider. Come to the poster to see what we could prove, conjecture, or construct regarding this parameter, and also how we use it to use stable sets in flex spheres to get an improved lower bound theorem for the number of faces in flex spheres. Thanks, bye.
Hello everyone, welcome to our poster presentation. My name is Fraser Getachew Kabede from Addis Ababa University, Ethiopia. Our poster title is An Involution on Derangements Preserving Exceedances and Right to Left Minima. This is a joint work with Professor Per Alexandersson from Stockholm University. The motivation of our work is to prove this identity, which is about the difference of even derangements and odd derangements that has k exceedances. We prove this identity using two methods. One is by defining an involution on the set of derangements. This evolution preserves exceedance value set and also right to left minima set, and it changes the parity of the derangements. We managed to prove the generalizations of the identity that we saw. In addition, we have another identity which concerns about the number of right to left minima. Another way of proving the identity is by using generating functions. So I hope to see you all.
About our poster titled Pigs Are Preserved Under Unsorting. My name is Olivia Nawanda from Makerere University, and this is joint work with Per Alexandersson from Stockholm University. What is interesting in our work? We basically look at what we call the run-sort function, and by run-sort of sigma, we mean rearranging the runs of a permutation sigma of length n in lexicographical order, as you can see in this example. And this run-sort function is found to have close connection with Bell numbers and descents. The main result in our work is the bijection that preserves the peaks for a permutation sigma of length n before run-sorting and a peaks or a permutation sigma of length n after run sorting. I hope to see you all. Welcome to our poster.
All right, I'm Colin Defont, and my poster is called Troops, Cumulants, and Stack Sorting. It's based on this paper called Troops, Cumulants, and Stack Sorting. And there are three objects that are appearing in this poster. One is the stack sorting map, which is this certain function that sends permutations of size n to permutations of size n. And then there are these objects called valid hook configurations, which look something like this. And then there are these things called cumulants, which appear in free probability theory. And basically, there are these two formulas that appear on the poster. One of them is involving basically stack sorting, and the other one is involving cumulants. But both of these formulas are given as sums over valid hook configurations. So you can combine the two formulas in order to use tools from free probability to say things about stack sorting and vice versa. There are also some open problems in the poster. I'm not in India, but the poster is available on my website here, and you can contact me by email if you have questions.
Hello, everyone. We are very happy to present our poster in Fpsac. The poster's title is Equidistributions around special kinds of descents and accidents via continued fractions. This work is joined with Dr. Jianxi Mao in Dalian, China, and Professor Jiang Zhen in Lyon, France. As we all know, the Euler polynomials can be interpreted by the permutation statistics, descent and accidents over permutations. Here we introduce another two permutation statistic, descent of type 2 and pure accidents. Our work is motivated by the conjectures of Baril and Kizov. In our paper, we prove the conjecture of Vajanovsky about the equidistribution results on Sn. We give more equidistribution results and open problems in our paper. Welcome to our poster for more information. Thank you.
Hi, my name is Shinan Gao. The title of my poster is Combinatorics of Neolithic numbers. This is based on joint work with Gidon Relowitz, Nicolas Rasser, and Alexander Young. So we'll be giving an exposition of recent developments in the study of Neolithic numbers. These are tensor product multiplicities of irreducible representations of classical groups in the stable range. The little Wolfsheim coefficients form a special case. And these are also a structure constant of the Kuoki-Torada basis in the ring of symmetric functions. So we'll be giving two types of combinatorial results of these numbers. Those that can be derived combinatorially from the definition of these numbers, and those that also employ geometric and representation theoretic methods.
Hi, I'm Jesse Kim, presenting work with Brendan Rhodes on set partitions, fermions, and skein relations. Our story begins with a famous transformation, shown here. It and similar transformations appear in a variety of areas of mathematics, such as representation theory, knot theory, and others. We studied a generalization of this transformation, to the case where crossings can occur not between just edges, but between blocks of a set partition that might be larger than size 2. When these blocks are larger than size 2, it turns out that the right thing to do is to add a few extra terms to these relations. We draw connections to diagonal co-invariant ring over anti-commuting variables, or fermionic variables in the language of physics, and use these generalized gain relations to give a combinatorial basis of this ring.
I'm going to talk about a statistic for regions of braid deformations. So we consider hyperplane arrangements, which is a collection of hyperplanes in a Euclidean space. And one would like to compute the regions of this arrangement. A formula was given by Zaslawski, which says that the number of regions is the sum of the coefficients of the associated characteristic polynomial. So for example, consider the braid arrangement. Here the regions are in bijection with the permutations, and coefficients of the characteristic polynomial count permutations according to number of cycles. So in our paper, we consider braid deformations. So these are arrangements which have hyperplanes parallel to braid hyperplanes, and the regions are in bijection with certain trees. So our statistic says that the coefficient of t raised to j is the number of trees with exactly j branches. Thank you.
Weighted Erhard series and a type B analog of a formula of McMahon, presented by Elena Tierka. The rational function with the Eulerian polynomial in its numerator is equal to the Erhard series of the unit cube. And by generalizing this to simplices, we obtain the descent polynomial over multiset permutations in the numerator. So in type A, we've seen a connection between multiset permutations and simplices. And the natural type B analog of this would be a connection between signed multiset permutations and cross polytopes. And indeed, this works. The numerator of the Erhard series of products of cross polytopes is a descent polynomial over signed multiset permutations. It can be even refined through a weight function on the lattice points and the major index. Using this, we study properties of this new descent polynomial by studying certain properties of the corresponding polytope. This and more can be found on arXiv.
Welcome, I'm Lucas Kühne and I'm talking about a joint project with Joshua Maglione on the geometry of Flag-Hilbert-Poincaré series for matrices. Josh Maglione and Christopher Wall introduced a new polynomial invariant of hyperplane arrangements called the cos-flag polynomial. It's motivated by a Gauss-Seidel function and obtained by looking at all flags in the intersection lattice of an arrangement. In the example on the top left, this polynomial is 32 times 1 plus 40 plus t squared. Our main result says that for a real arrangement, this polynomial normalized by the number of chambers of A is lower bounded coefficient-wise by the Eulerian polynomial. The equality holds if and only if the arrangement is simplicial. And in the example on the top left, the arrangement is simplicial, so this polynomial is exactly 32 with the number of chambers times 1 plus 40, the same Eulerian polynomial. We conjecture that this is real root in general, and our result also holds for oriented matrices. Thank you very much.
Hello, everyone. My name is Kyle Saloy, and this is Inequality of a Class of Sure Q Functions. So this project was done in the attempt to answer part of the question of when two skew Sure Q functions are equal to each other. The technique we used was decomposing these into the non-skew Sure Q function basis. And you can see on the top right there are the Littlewood-Richardson style rule in the case of these shifted partitions. In particular, we were looking at a class of diagrams called frayed ribbons, which are ribbons with a single box attached on the staircase that you get when you do the shifting of the diagrams. And our conjecture is that all of these shapes actually have distinct Sure Q functions from each other. So in the bottom right, we have sort of our three main results. You can distinguish these diagrams by the number of turns that they have. Those give you distinct Sure Q functions. And then within a certain number of turns, you can also, distinguish these cases from each other. So our goal is to extend this work, and thank you for checking out this poster.
My name is Reuben Hodges, and I'm a postdoc at UCSD, and I'm presenting our poster, Classification of Levy Spherical Schubert Varieties. This is joint work with Yibo Gao at MIT and Alexander Yong at UIUC. Spherical varieties are a generalization of toric varieties that arise in combinatorial algebraic geometry and are heavily studied. Another class of varieties of significant interest are the Schubert varieties. Our project asks which Schubert varieties are spherical varieties for the action of a Levy subgroup. We give a classification of these Levy spherical Schubert varieties in type A. The proof relies on and contributes to the theory of key polynomials. Along the way, we encounter permutation and composition pattern avoidance, split symmetric polynomials, multiplicity freeness, and Coxeter combinatorics. We conclude with a new general type conjecture for classifying these Levy spherical Schubert varieties and provide supporting evidence.
Hi everyone, I'm Torrin Greenwood, and today I'm going to tell you about my work with Steve Meltzer, Tia Ruza, and Mark Wilson on asymptotics of coefficients of algebraic series via embedding into rational series. And so in analytic combinatorics, a common goal is to figure out asymptotics of a sequence that you care about. And so you might start with a combinatorial description of the sequence. You can use the symbolic method to embed this into a generating function, and then you can use complex analysis to pull out asymptotics from the generating function. I care about this last step right here of pulling out information from the generating function, specifically for algebraic generating functions. And so those encode things like dict paths or Motzkin numbers or numbers of RNA secondary structures. And the key idea here is that we can use an algorithm called Furstenberg's algorithm to embed an algebraic generating function into a rational generating function of more variables, which allows us to use pre-existing asymptotic results. If you want to learn more, please come and talk to me or email me. I'd be happy to talk about it. Thanks.
Hi everyone, this is Om Prakash Bharadwaj, PhD student at i.i.d. Gandhinagar. The title of my poster is Affine Semigroups of Maximal Projective Dimension. This is joint work with Professor Ananda Sengupta and Dr. Vritti Goyal. In this article, we study the affine semigroups whose associated semigroup rings have maximum possible projective dimension. In short, we call these semigroups as NPD semigroups. It is known that these semigroups have a non-trivial set of pseudo-Frobenius elements. Therefore, similar to the numerical semigroups, we generalize the notion of symmetric and pseudosymmetric semigroups to the MPD semigroups. And under suitable conditions, we prove that these semigroups satisfy extended width conjecture. We also study the row factorization matrices associated to pseudofrequency elements of MPD semigroups and study a relation between the defining ideal of semigroup ring and the row factorization matrices of pseudofrequency elements. Thank you.
Hello, I'm Ji-hyuk Jang, and I'm a graduate student at Songyongwan University in South Korea. The title of my poster is a combinatorial model for the transition matrix between the fetch and web bases. And this is a joint work with Byung-hak Hwang and Jae-sung Oh. As you can see from the title, we provide the combinatorial interpretation for entries of the transition matrix between two bases of the irreducible S2n representation indexed by n, n. To do this, we introduced a new class of permutations called web permutations, and we also study enumerative properties of these permutations. I'm sure that many of you are interested in our research. Thank you.
We introduce a family of univariate polynomials B lambda indexed by integer partitions. These polynomials have the interesting property that at 1 and 0 they count the number of set partitions and standard tableau of shape lambda. Moreover, at -1 they count the number of standard shifted tableau of shape lambda. For instance, when lambda is 331, there are precisely 4 such standard shifted tableau. The Stirling numbers of the second kind can also be expressed in terms of these polynomials B lambda. One way to define these polynomials as B lambda is by using an interlacing statistic on set partitions. An interlacing of a set partition is simply a crossing of jth arcs for some j. For instance, when A is the partition 1, 2, 9, 3, 8 and 5, 6, we plot these points on a line with one point at infinity and draw the arcs corresponding to 1, 2, 9, 3, 8 and then 5, 6, and there are precisely two interlacings in this case. The polynomial B lambda is obtained by summing Q to the number of interlacings of A as A varies over set partitions of shape lambda.
Hi everyone, this is Zero-Hecker-Clifford modules from diagrams. The representation theory of zero-Hecker and zero-Hecker-Clifford algebras can be understood in terms of quasi-symmetric functions, and our goals here are to give a general construction method for modules of these algebras in terms of tableau diagrams and give some applications of this. The construction method proceeds by fixing a diagram of n boxes in the plane of any shape you want and choosing any subset of the n factorial different fillings of the boxes. If this subset satisfies a condition we call ascent compatibility, then we get the modules we desire, and we also have formulas for their characteristics in the algebras of quasi-symmetric and peak functions. For applications, we can construct modules whose characteristics are the quasi-symmetric Schur-Q functions, modules whose characteristics are a new basis of the peak algebra, analogous to the quasi-symmetric Schur functions, and we can also provide a general framework for zero-Hecker modules whose characteristics are notable families of quasi-symmetric functions. If you'd like to know more, please get in touch or check out the paper on the archive.
I am Nishu Kumari from the Indian Institute of Science, Bangalore. The work Factorization of Classical Characters listed by Roots of Unity is jointly done with Professor Arvind Iyer. Earlier by Littlewood and independently by Prasad, Schur polynomial was considered with the specialization x omega x up till omega to the power t minus 1x, where x is an n-tuple of commuting indeterminates and omega is a primitive t-th root of unity. They showed that the Schur polynomial is non-zero if and only if the t-core of the index partition is empty and the non-zero character factorizes into characters of smaller groups. We generalize their results to the classical groups of type B, C, and D. In the symplectic case, we characterize partitions for which the symplectic character is non-zero in terms of what we call symplectic partitions, and we also show that the non-zero character factorizes into characters of smaller groups. Thank you. Welcome to the poster.
I'm Matthew Plant. This is joint work with Sergio Elizalde, my advisor Tom Roby, and Bruce Sagan.
we study the dynamics of iterating row motion on fence posets. A fence poset looks like a dict path where shared elements connect the segments, and each fence poset can be uniquely described by the number of unshared elements in each segment. Row motion is an action on order ideals or sometimes anti-chains that has received a lot of attention over the past decade. We can think of it as this three-step operation. Orbits of row motion for general posets tend to be quite wild, but for fence posets, we have a nice way of representing them as three-color tilings of a cylinder satisfying certain conditions. We find interesting statistics that are linear combinations of indicator functions of poset elements, which have the same average over each orbit. Such functions are called homomessic statistics. For anti-chain row motion, the difference of indicator functions of unshared elements in the same segment is zero-messic. Here's another example of a homomessy. Tom Ruby will be presenting the poster in Bangalore, but I'm also happy to discuss the results with anyone who's interested. Thank you for your attention.
Hi, my name is Jonathan Boretsky, and my poster is titled The Totally Non-Negative Complete Flag Variety and the Totally Non-Negative Complete Flag Dressian. A number of authors, including Reach, Talaska and Williams, Lamb, and Lustig, have observed that a subspace lies in the totally non-negative Grassmannian, as defined by Lustig, if and only if all of its Plucher coordinates are non-negative. We extend this result by showing that a complete flag lies in the totally non-negative complete flag variety if and only if all of its Plucher coordinates are non-negative. We also study the tropicalization of the complete flag variety. There are two seemingly reasonable definitions of the tropicalization of the complete flag variety, depending on which of its defining equations we decide to tropicalize. In general, these two spaces differ, with one, the tropical complete flag variety, being strictly contained in the other, the complete flag Dressian. However, we show that the non-negative parts of these spaces, the totally non-negative tropical complete flag variety and the totally non-negative complete flag Dressian, coincide.
Okay, thank you. Thanks to all the, let us thank all the poster video presenters. So there was a suggestion from the previous chair that the entire Fpsac could be like this. Rest all time for discussions. Okay, so shall we move to the posters over there? Please take your stuff with you and remember to fill out all the forms that I mentioned earlier.